Okay, hello everyone.
Hello, good morning.
Hello, do you hear me? So it's good. Today is the Monday, July 11th, so we start and continue our BEGO school session of Monday. Today we have a tight program with a lot of speakers on the session named Cocoon and BDHN models, so it's mostly dedicated to the GRB part. And this week will be mostly dedicated to the GRB part. So the first speaker today is Maria Giovanna DAINOTTI. So Professoressa DAINOTTI, do you hear me? Can you connect? I see you in the participants list, so, but your microphone is off. If you can connect, then switch on your microphone.
Can you hear me?
Yes, I can hear you. So you can share your screen and...
Yes, thank you. Okay. Can you see? Oh, sorry, I think that's wrong.
Okay, we see your screen.
Okay.
Okay, it's a full screen. So again, today we have the first talk by Dr. Maria Giovanna DAINOTTI, okay, associated with the University Division of Science in Tokyo, Japan, Space Science Institute. So, Professoressa DAINOTTI, the stage is yours, and go ahead.
Okay. Thank you very much. I would like to thank the organizer for inviting me today to speak about the 3D fundamental plane correlation for nearly 180 gamma ray bursts in optical afterglow. And I would like to briefly tell you the outline of my talk. I will introduce gamma ray burst, then the X-ray luminosity time correlation involving the Plateau emission and its application to GRB cosmology, the 3D fundamental plane involving the Plateau emission and its interpretation, then the luminosity time correlation in optical and its extension in 3D, the 3D optical correlation. Then I will compare it with the X-ray time correlation, and I will tell you a little bit more about the achromaticity of the Plateau emission. And then I will draw conclusion, but also the ongoing projects with the 3D fundamental plane correlation in optical, which has been recently accepted as a PJ supplement paper, and the future projects that are ongoing with the Kiso telescope, which is located here in Japan, in Nagano. First of all, I would like to tell you a little bit about the GRB phenomenology. And here we have a nice light curve that represents gamma ray burst observed with the Swift telescope. Here we have that the blue line is the phenomenological Willing et al. 2007 model. And here I would like to point out that these GRBs represent the gold sample. So gold sample is a class of GRBs that I will point out later in my talk. GRBs, as you all know, are flashes of high energy photos in the sky. Their typical duration is from few seconds to in the prompt emission, but they last up to several weeks or even months in their counterpart, which can be in optical and in radio bands. The most frequent is in X-rays. And since they are so much extremely energetic, they can release in a few seconds the same amount of our energy releases in its entire lifetime, and they can observe up to Redshift 9.4. So we all know that classification of GRBs is very, very challenging, but somehow we all come up to the classification between a short and long gamma ray bursts, where short GRBs, they come from the compact object merger, neutron star black hole, and their T90 is less than 2 seconds, while for the long gamma ray bursts, we have T90 greater than 2 seconds, and they are driven by the core collapse of massive stars with stars that are more massive than 30 solar masses. But this classification is sort of outdated, and we have new classification, the Norris and Bonnell 1 in 2006, in which the intermediate class of GRBs with mixed properties have been have been introduced. And so this is also important in the classification for correlations to understand well which classes we are dealing with. In fact, this short, long classification comes from the Batze definition of the hardness ratio. But why gamma ray bursts are so appealing? They are appealing also because they can be used as cosmological tools, because they can be probes of the early evolution of the universe. They are observed beyond the epoch of ionization. They allow us to investigate population tree stars and to track the star formation. They are much more distant than supernovae 1A and quasars, but there is a huge problem with them being standard disabled candle because they don't seem to be standard given that their isotropic prompt luminosities span over 8 orders of magnitudes. In fact, here we can clearly see the huge step that you have in the logarithmic of redshift. And in fact, there is a 4.4 up to 6 actually discrepancy between supernova 1A and Planck observation regarding the Hubble constant. So gamma ray bursts, in fact, they can help to reduce this tension. Now, in fact, there is a very nice common motto in the GRB communities that says that for 20 years, we have been really struggling to understand what it is the light curve feature, like common feature of GRBs. And we used to say that what it is the common feature of GRB? Well, if you have seen one GRB, you have just seen one. So how to use gamma ray burst as standard candle? And here we have a Swift light curve taken from the Swift repository. You can see that the light curves vary very widely. Now, I like calling this problem the GRB zoo. So which GRB class works the best as a standard candle? Well, the bad news is that none of them really works alone as standard candle. But the good news is on the way, and please hold your breath for a moment and I will tell you later. So one of the key points of my study as well as in my group is to try to standardize them. So we know that the X-ray flashes have the typical duration that it is similar to long GRB, so it is greater than 2 seconds, but they have the gamma ray fluence over the X-ray fluence over the gamma ray fluence, which is greater than 1. The GRB associated with supernovae, mainly 1BC, again, they have the typical duration greater than 2 seconds, but the X-ray fluence over the gamma ray fluence is less than 1 compared also with other cases. And I would like to point out also the ultra-long gamma ray burst for which the typical prompt duration is greater than 2000 seconds, while for the short with extended emission, we have mixed feature between short and long with the duration, the prompt emission, which it is less than 10 seconds. And in one case, in the sample, we have the presence of the supernova or optical bumps. Again, this classification inside the study of correlations, it is indeed very important. Possible reliable candidates are the luminosity time correlation in the afterglow emission and the peak luminosity in the prompt emission versus the end time luminosity at the end of the plateau emission. Now I would like to start with the luminosity time correlation in X-ray. Here we can see that this correlation is roughly -1. So it means that the energy reservoir of the plateau stays constant, and the correlation has been updated in over the years with many papers. But what I would like to point out here is that one can see that there is a trend of this correlation that steepens out the correlation slope. So one needs to pay attention to what it is the intrinsic slope of the correlation to use it as a standard candle. And I would like to point out that there are methods that have been dealt with the Efron and Petrosian method, which Professor Petrosian will speak at the end of today, how to correct for selection bias and redshift evolutions. And here again, we have, so this correlation, it is intrinsic to selection bias and redshift evolutions. And I would like to point out a second correlation, which is the correlation between luminosity at the end of the plateau emission and the peak prompt luminosity. Again, for this correlation, we considered several redshift beams and we checked whether or not this correlation evolves with redshift and how we can correct for selection biases. Now we can see that both those correlations, indeed, in those two papers has been demonstrated almost 10 years ago, that they are intrinsic to GRBs and not due to selection biases. Then safely, we can use those correlations to extend the Hubble diagram up to Redshift 9.4. And these papers, indeed, they consider this application for as a cosmological tool. Now, we would like to have a further hunting of the GRB correlation. So what can we do further? As I have already pointed out in one of the previous slides, there is a subset of gamma ray burst for which we can clearly see the supernovae associated. But now the point is that we want to understand whether or not this class of GRBs, they behave similarly in terms of obeying this correlation to the other classes. So here we have the long GRB for which no supernova has been associated at small redshift, which are this triangle downward, and the triangle upward in red are instead the GRB associated with supernova. And here I would like to also mark down the remarkable case of 980425 that has an indication of the plateau emission and still stays on the correlation line. But here I also would like to point out that this correlation is 2.8 sigma away from the -1 correlation. So the slope of this GRB supernova ABC class, which are the most, which are the ones that are spectroscopically associated with supernovae, then the plateau energy reservoir may not be constant. Of course, this is like a sample with small, it's a small number of GRBs. So we need to consider like a larger sample to whether or not to confirm these results. And the GRB supernova connection, in fact, is an important, one of the important pillar point of one of the future ongoing projects recently. Now, when I mentioned about the 2D correlation luminosity at the end of the plateau emission versus the time end of the plateau emission, and then luminosity at the end of the plateau emission versus the peak prompt luminosity, then we can see that this when you combine those two correlations, you obtain the 3D fundamental plane relation. And this is the main topic of my talk because it runs in X-rays, but it has been recently confirmed in optical as well. And this has a reduced scatter of 24% compared to the full GRB two-dimensional correlation in X-ray. Now, of course, one can argue that this correlation, maybe it's due to selection biases, and it is not the gold sample, it's a subset of GRBs, as I mentioned before, for which we have a relative, not so steep plateau, less than 41 degrees, minimum 5 points at the beginning of the plateau, but then we have a reduction of the intrinsic scatter of 54% when we compare this to the 2D sample. So what can we do? We can actually run 10,000 to check whether or not this is due to selection biases. We can run 10,000 Monte Carlo simulations showing that the probability of obtaining such a sigma intrinsic scatter by chance is really very small. It's 0.3%, so it's much smaller than 5%. So definitely this is not a selection of the sample. And then we can see this 3D correlation as a 2D luminosity, peak prompt luminosity correlation versus the energy reservoir of the plateau. And we can draw a conclusion, say that the more powerful the prompt emission is, the more energy is released into the plateau phase. Here the slope of the correlation is 0.59, so it's roughly 1/2 in log scale. And if we would like to compare this relation with the other 3D, this correlation is much tighter than other correlation that appeared in the literature so far. So the luminosity time peak plane is smaller by 36% of the luminosity time EISO correlation. And of course, we were driven to continue investigating this correlation, trying to understand whether or not the classes of GRBs can really pinpoint another fundamental plane. And we can see definitely that the short GRBs with extended emission, they follow a different distribution of the gold GRBs from the gold fundamental plane. So this is the zero axis is the reference placed in zero for the distances of the gold fundamental gold GRBs from the gold fundamental plane. And for the series of these papers, I was named then Marie Curie Fellow of the Week, and there were several press releases by INAF, Scientific American, and the AAS. Now, what does it mean to have these two different planes? What it means is that probably there are two different classes that are driven by different parameter space within the magnetar scenario. So if we consider the spin down luminosity of the magnetar entirely being within the theta jet, then we can see that the long and the short GRBs, they placed differently in this diagram, in the magnetic field spin period diagram. So you can see that the long gamma ray bursts, they are placed with the smaller spin period and the smaller magnetic field compared to the short GRBs with extended emission. Of course, there are outliers. And again, another point that I would like to develop in the future is to consider not only short and long classes, but also the other classes. And of course, this result can be extended, and I will tell you in a moment, also considering the external shock model. This was a paper done in collaboration with the summer student from Stanford University. And if you're interested in a more complete review of the correlation, GRB correlations, their application as cosmological tools, and how the selection biases have been discussed, then you can see this series of papers. These are reviews which are gathered, summarized, and expanded in the paper, in this book that was published in 2019 by IOP collection. Now I can summarize the first conclusion of the talk, in which we have that the 3D correlation for the gold sample, I'm speaking about the X-ray correlation, has a sigma intrinsic scatter, which is 54% smaller than the long gamma ray bursts for the same bidimensional luminosity and correlation. This induces the fact that it implies that it is the tightest three-parameter correlation, including the Plateau phase, and the statistical difference of the planes of short and long gamma ray bursts implies also a difference in the magnetic field spin period diagram of the magnetars. This correlation also holds for Fermi GBM burst. But now I would like to go to the core of my talk, saying that if you are ready or not for the big news about the optical extension of this correlation. And first, we want to say a bit more about how we can go from the gold sample to the platinum sample, which is a subset of the gold sample obtained after removing gold GRBs with at least one of the following features. So the time at the end of the plateau emission inside a large gap of the data must be excluded. We also want to exclude plateau duration that are less than 500 seconds and that they present gap after it. And also we want to consider flares and bumps at the start and during the plateau phase. So this reduces the scatter of 31%. So we obtain intrinsic scatter of 0.22. Now this is the fundamental plane for the new classes, and we also can point out the kilonovae, the GRBs that are associated with the kilonovae that are represented by this rhomboid in this projection of the 2D, of the 3D correlation in 2D. And also these cases have been presented by Rossi et al. 2020. So if we consider the temporal power law decay index after the plateau, we can see steep decay, and this indicates the internal origin of the plateau if you consider this alpha that is greater than 4, as pointed out by Li et al. 2018 and Lyons et al. 2010. Now, regarding the GRB fundamental plane in X-ray and this association with the kilonovae, we can see that these short GRBs associated with kilonovae, they lie below the fundamental plane. And when we see these distances from the fundamental plane, we can see that indeed the short GRBs associated with kilonovae, they are the largest, I mean, they are much more different from the gold sample. And I would like also to point out that this is the new class of platinum sample, which, being a subset of the gold sample, of course, it aligns and agrees with the platinum, with the gold sample. Now, here it is, one may wonder why we have two panels of those, the same picture. The upper panel is without the correction for selection biases. The lower panel is when we consider the selection for the correction for selection biases. And we can note that with the correction for selection biases, actually this difference is even more pronounced. We did indeed the zeta score computation, which is summarized here. And here we can see that the greater zeta score is for the long GRBs associated with supernova events, and the kilonovae as the highest one, even before and after the correction, as you can see. Now, why it is important, I'll tell you in a moment, because this is again related to the optical correlation. But if we want to test the closure relationship between temporal and spectral decay indices and their connection with the fundamental plane, because as you may remember in the beginning of the talk, I mentioned that one of the goals is to use GRBs as cosmological tools, but we need to have a model, so a supportive theoretical model behind this subsample of GRBs that could drive this as possible standard candles. And one of the most fulfilled closure relationship, it implies wind slow cooling. The smallest scatter, it's sigma int 0.29, but this is slightly larger than this platinum sample, and this is related to fast ISM or wind medium. Now, as I promised, this GRB correlation, luminosity time correlation in optical is valid for more than 100 GRBs, and the gold sample definitions work also for the optical sample. One point is that unfortunately, the platinum sample cannot be derived for the optical correlation, because we have still not so many GRBs that present the peak of the prompt luminosity in optical data. This is one example here. And again, I told you that I would tell you a little bit more about chromaticity versus achromaticity of the Plateau emission. And here we can say that the Plateau is achromatic between X-ray and optical for 56 Swift GRBs through the t-test. With the new paper just accepted, we could even confirm this result with 89 gamma reverse. And this is the sample of the 2D correlation for all gamma reverse, so the slope is compatible with -1, and for the gold sample, again, it is compatible with -1, also in relation to the X-rays. Now, again, we stress the importance with the GRB supernova connection, and I already mentioned before this ABC classes for which A has a strong spectroscopic evidence with the supernovae. The B class has a clear light curve bump as well as some spectroscopic evidence resembling the GRB supernova, and a clear bump consistent with other GRB supernova at the spectroscopic redshift of the GRB. Now, what can we do? Because the classification is really large, and we want to distinguish between type 1 and type 2 classification. And here there is this famous classification by Bing Zhang in 2009, in which some of the classes have been gathered together. So the type 1 are mainly the short GRB, and which we can put the short GRBs with extended emission and the ones associated with the kilonovae. The type 2 basically are the long gamma ray for which the association with the supernova is seen, and they reside in galaxies with high star formation rate. They explode in the same location where the progenitor stars are formed, and they are also more characterized by stratified stellar wind type medium. Now, if we would like to consider the other classes in the zoo separately and together with type 1 and type 2, we can see basically that there is no particular clustering of these classes in comparison to the 2D optical correlation. And even if we consider the angle of the plateau emission, does not appear any clustering, as well as the T90 in the prompt emission. And I would like to stress again that this result that was indeed fulfilled for 100 GRBs, when we extend the sample of almost doubling the sample to 180 GRBs, this result stays the same. So here are the differences between the classes for this almost 100 GRBs, and we can see that this is similar to what we have been confirmed with 180 GRBs. But now, here we have the working progress, because we still look and we still looking forward to have the standard set of gamma ray bursts. And now, in this updated paper, actually, we have that the flow diagram is the following. So first, we gather the photometric data, then we convert them in a singular band, the R band, and then we perform the extinction correction. Then we perform the light curve fitting with 3 different models, because in previous analysis, we focused on William-Geltard 2007 model. But in this new updated analysis, we also fit with the simple broken power law and with the smooth broken power law. So to give more credibility and reliability on the modeling versus the light curve fitting, because this model has the backup of the standard fireball model. Then we analyze statistically this sample with and without the correction for selection biases with the Efron and Petrosian method, and then we investigate the chromaticity of the TA optical versus TAX, then the 2D relation and the 3D correlation. And in addition to what we have done previously, we consider also the Anderson-Darling test and the Anderson-Darling test for normality. Those 2 tests, actually, they tell us whether or not this correlation, it is really intrinsic to GRBs, because we should have that the residual of this correlation should be normal. And those 2 tests, actually, the correlation passed those 2 tests. So the test is telling us that if the correlation is statistically significant, then the correlation theoretically should agree with the luminosity at the end of the plateau emission, that it is derived from the observable. Now, I think I have only probably a few minutes left before the question. So I would like to tell you a bit more about this web page development and the involvement with the Kiso observatory. So here we are in this future to-do list. We are building a package for building the largest optical repository to date for the light curves, optical light curves with known redshift. So here we take the GCN, and then we store all the data from a given GRB. We parse tables and sentences, and then we parse for fluxes and magnitude. And here again, as I mentioned, through this tool of the repository, we managed to extend the sample of the 2D relation up to 180 and to extend the 3D correlation up to 58 GRBs, for which we see that the correlation exists. Here, I would like to point out some difference with the previous analysis, in which we see that there is not a remarkable difference between all classes, except with the classes of the supernovae and the X-ray flashes. So here there is the difference and similarities among all classes in the 3D fundamental plane, and with the darker line, it is indicated the corrected classes. Now we can see that there is not a clear distinction between the classes, although in some cases we see some distinctions at the 2 sigma level. But now, as I promised, and this is motivated by Samuel Young, a student that was working on this in summer of last year, we are creating this plotting and cleaning of the light curve. So you can see here that the band is represented, and then we can accept or reject the current data points. And after we have this rejection and acceptance of the data point, we can perform the fitting, and here it is the delta chi square as a function of the singular variables. And this is I'm now showing for the Willinger function, but the web page will implement also for the smooth broken power law and for the broken power law. And here you can see the interface is very friendly. It is done in a Python package, and you can see that you can put basically your guessing parameter, and then you can on the go convert the fluxes, accept or reject the data point, and then attempt to do the fitting. And now I would like to present the new gamma ray burst optical repository. This is the web page that we are building. This is done with the Streamlit, and you can see that you have a GRB quick view. Then you can have bulk download if you want to have the data from the original sources, from the GCN and from the ADS search. Then you could download those. And then instead, if you're interested in the fitting and you want to have already them transformed in erg centimeter square per second, then you would go and find the GRB in this other window. So you see here we have the information of the right ascension, declination, and the redshift, and we are planning to add also the spectral index. So this is ongoing. Now, I would like to give you, with this 1 minute left, I would like to show you how the repository look like more in detail. So you can see that you can search for the information of the GRB, then you can fit this. You can run actually MCMC, and then you can decide which model you want to run. Then you see you have this time, flux, and alpha that you can change according to what you think they are most plausible guessing parameters. And then you have to wait for some moments to load this result that eventually will give you the fitting in already in the web app. And after you do that, you can also we are going to provide the full table for that. And you can see that here you have another part of the repository, and I will just go here on the end of repository. Sorry, on the fit statistics. So you can see that you have the fit statistics, the variables that have been given, the correlation, and then you can have the picture of your fitting with the residual. So if then you are not happy with your fitting, you can rechange the parameter space and you can refit again. And then as a last information, there is a nice manual for which you can go and check how this routine is built, and therefore you can continue working on improving this. And now, as promised, I would like to tell you also about the importance of the Kiso Schmidt telescope to the current study. And actually, this is an invitation for all of you. If you would like to participate to this project about building this largest optical catalog to provide additional optical light curves that you have, you're very welcome to join this project, because at the end, we would like to study the temporal indices and try to understand if there is some common driven mechanism that can be used with the largest optical catalog. Now, why we wanted to include also the Kiso Schmidt telescope for the current study, because is my time ended?
No, you still have 10 minutes around.
Okay, perfect. So due to the large field of view capability of the Kiso telescope, so we will able to follow up the interplanetary network and the Fermi GRBs, because as you know, one of the key points is that while majority of optical telescopes, they follow up the Swift GRBs, there are not so many that have the capability to follow up the Fermi GRBs. So then we can build up a self-consistent afterglow plateau with crafted pointing strategies. So we can identify new plateau emission and we can reduce the uncertainty on the error bar. So if we would like to first consider the feasibility study for the potential use of the Kiso telescope. And by the way, we have already started this campaign with the seven detections, and one GRB is the New Year GRB that has been really observed. So we have 27% of observation 100 nights observed by Kiso. 50% will be happening during the night, then 70% will be visible, 30% will occur in the southern hemisphere. So the fraction of GRBs with optical plateau that we can observe is 38%, and the probability of observing all optical GRBs, it's 9%. So the probability of observing optical GRBs with plateau is around 4%. Now, we have spoken about the classes of GRBs, and then we can say that we will have 8 GRBs with plateau, but 20 GRBs per year. And based on probability of 20 years of observations, then we have 1 kilonova every 0.2 kilonova basically per year, 13 between X-ray flashes and X-ray rich, 5-6 GRB supernovae, 7-8 long GRBs, 2 short, and almost 1 ultra long and 1 and 2 gold sample. Now, if we would like to check the limiting luminosity of the Kiso telescope, definitely we need to integrate for 1000 seconds to have that almost all the GRBs could be observed with this limiting observing facility. So once again, if you have a telescope on your hand and you are interested in joining the project, this will be very helpful, because eventually we will gather the data points, several data points from different telescopes to build up the light curve. And another point that I wanted to stress, because in the 180 GRBs, we also included 18, so roughly 10% of GRBs that were included by the Subaru telescope. And again, since I'm located now in Japan and NUJ, if you want to participate in an observing proposal, I can BPI for that. So if you have interest in science, please also contact me. In this regard, for example, the Subaru telescope could pinpoint some cases in which the GRB plateau emission was indeed not seen by other instruments, and those points are, strategically located within the gap. So we can help the analysis with filling the gap in optical light, which provide more precise spectralist feature and redshift determination, identify new plateaus, and reduce the uncertainties in the error bars. And this is the team that willing to, connect with other telescopes in the world. Now, I also mentioned that the plateau emission can be seen also in high energy, and we have 3 cases of LAT gamma ray bursts that follow the 3D DAINOTTI relation. And here, those are compared to the rest of the distribution in X-ray, they are at the high end of the distribution, so smaller values of the time of the plateau emission. So now, if we want to conclude this toward the standard candle, so that we can say that the gold GRB reduces the sigma by 54% compared to the 2D luminosity and correlation. The platinum reduced further this sigma by 31.3%. The GRB kilonova sample has a comparable sigma compared to the platinum. The zeta score among those classes of short GRB kilonova, short and short with long GRBs, have a different plane compared to the gold, and short kilonova are always below the short fundamental plane. So these results are confirmed once evolutionary effects are accounted for. Luminosity time correlation in 2D and in 3D holds for optical. And actually the good news is that when we apply it for cosmological purposes, this can be actually a good standard candle. So we can match theory and observation, and this is again another project that is ongoing regarding the optical closure relationship. And as I mentioned, for the future goals for the Kiso is to enlarge the sample with more classes, but especially we are interested in the observation of short GRBs. In fact, together with the Swift, we can and Fermi, we can actually double the sample of short GRBs observed in a year. And also, although we have only small probability to observe one ultra-long gamma ray burst with Plateau, since the ultra-long GRBs and very long GRBs are very peculiar and there are not so many to be observed, this is also a challenge that we would like to take. And thank you very much for your attention, and you are invited to join us. Thank you.
Okay, thank you. Thank you for this very informative talk. So if someone has a question, there's a perfect time in 5 minutes to ask.
Well, this was a very, very impressive talk, and of course open the collaboration on this with Japan, and the great opportunity that Maria Giovanna is in Japan. And we are going to present today, tomorrow, and these last 3 days, many, many news about the optical, radio, and JEV and MEV radiation in some selected object, especially in this alternative way which we have to describe GRB, the binary-driven hypernova of type 1, of type 2, and type 3. And in fact, some of the results of Maria Giovanna have been utilized, and we will enter into great details. I think we are making an effort also to, and it's good that the chairman of the session today is Yerlan, because Yerlan is working in AMATI, which is relatively close in between Europe and Japan. And I hope very much that he being an observator, work in the observatory in AMATI, will be able to, and the Russian telescope will be able to collaborate with you and with all of us in these activities. Therefore, it's very good that Yerlan is chairman of this session. Well, we have many news. We have also some problem because some of our people have been affected by this sickness. Therefore, we have to overcome this difficulty. But I promise, Maria Giovanna, to keep in touch.
Yes.
And to collaborate.
Thank you. Thank you so much. Yes, we have enjoyed also the collaboration in these 2 papers of Li Liang, who is present today, and he was also important. He had an important role in our analysis, providing some of the code and many of the light course. So I was enjoying collaboration with him. I think there is a question by.
Yes, there is a question by Soroush.
Yes. Can you hear me?
Yes.
Okay, thank you for the very interesting talk. Actually, my question is coming back to that percentage you mentioned about this follow-up observation. I think you said 10% of the gamma ray burst has some follow-up observation. Can you please give some criteria for observing or follow-up observation of this ground-based telescope? Is there any affluence or flux limit for that, or something else? Can you?
Yes, actually, I mean, the 10% was the number of GRBs that were observed by Subaru that presented, optical data that we could add to the pre-existing data. And some of them, they were filled in the gap. But for example, if you want to have a strategy to understand how many seconds you need to follow up and for, what it is the minimum limiting flux that you need to have, you can consider your sample. This is like a rough rough computation, but and it has been done with 100 GRB, so we need to update this with the newly gathered 180. But basically, you consider the red line, that it is the maximum, the minimum flux limit that your telescope could observe in a given band. Then you want to integrate according to how much time you have for the observation. You may want to integrate for longer time so that you are able to observe fainter objects. So from the computation that we did with the Kiso, we now know that we have to integrate at least for 1,000 seconds if we want to reach this limiting line. If we integrate, because we can reach the magnitude of 21.3. So if we reach this 21.3 magnitude, then we will be able to observe majority of GRBs. As you have seen, only two cases are within this line. So if our goal is to observe for example, the Plateau emission, because I was speaking about the Plateau emission, this is the strategy. But for example, for the short GRBs, we need to have to point for, we need to be able to immediately point to the GRB, because as you know, the short GRB faint very rapidly. So the strategy, it's different in the sense that you would need to follow for longer time in the beginning, but also you have to have more frames in a shorter time. So the strategy depends on the telescope. So the answer to your question, the strategy depends on the telescope that you have, but also on which target you want to observe, short or long GRBs. And if it is short GRBs, you just start to right away, once you have the alert, to follow them. In fact, in this kind of observations, we have already the alert built for the Swift and the Fermi GRBs. So if, again, you have some telescopes, then we are also willing to share some of the coding that we did for the fast alert.
Okay, yes, sure. Actually, just as a short comment, because this Iranian telescope, 3.4 meter, also one of the goal is observing these transient sources, and that would be great if we keep in touch in the future.
Yes, definitely. Yes, and of course, once you have the number of GRBs observed per year, then you can have the sketch of how many of the classes you are interested on you can observe, and then according to how much time you have, then you can decide also which is the most compelling science goal that you can do with your telescope.
Thank you.
Thank you so much.
Okay, so since we need to move on, the other questions should be discussed during the break, I guess.
Okay.
Maria Giovanna, I alert you on a very important result that Liang Li will present.
Yes.
And make sure that you, the day after the last day, make sure that you and your student will follow.
We will attend, yes. Thank you very much.
Bye-bye.
Okay, so the next speaker of the session is Professor Lorenzo Amati from the ENAF of Bologna. So Professor Amati,
hello, good morning.
Yes,
can you hear me?
Yes, we hear you and we can see your slides. Okay, so the stage is yours and go.
Thank you very much. It's my pleasure to give you a short overview of the potentialities of gamma ray burst for cosmology, which the previous talk by Maria Giovanna already mentioned. So I will go into a more wide overview of this very intriguing field of research. So, okay, as we know, just to summarize, thanks to many tens of years of observation and theoretical efforts, we know that we have two main classes of gamma ray burst, short and long. There are, of course, other subclasses, which is a very first-order classification with a general paradigm of long gamma ray burst connected to the core collapse of massive stars, and short gamma ray burst, at least a good fraction of them produced by neutron star mergers, but especially for cosmology, in addition to the progenitor, which is still a matter of debate, and we know very well all the researches in this field by the group of ICRANet. Also, the redshift distribution is very important, with long gamma ray burst being detected up to a redshift of more than 9, whereas short gamma ray burst at least a redshift of 2 or 3. So let me focus first of all on the high power of long gamma ray burst for cosmology. In a way, the idea is to fully exploit the huge luminosity of these phenomena that makes them detectable, as I said, up to the very early universe. So a redshift of 9 or more means a few 100 million years after the Big Bang, when the first stars and first galaxies were forming, when the universe was starting to be ionized. And just to give an example, it is the region of space time at which also the JWST is aiming at providing a substantial exploration. So the use of gamma ray burst for cosmology is mostly focused on 2 lines of research, as I mentioned. First of all, full exploiting long gamma ray burst for investigating the early universe. And on the other side, as Maria Giovanna mentioned, on one aspect of this research is to exploit gamma ray burst also for measuring the expansion rate geometry of the universe. So in other way, measuring cosmological parameter, investigating the Hubble constant tension, investigating the possible evolution of dark energy and properties, or alternative cosmological scenarios. So let me focus first of all on the first item, which is fully exploiting long gamma ray burst for investigating the early universe. This is a sketch representing the timeline of the evolution of the universe in the standard cosmological model. So in a few words, as you know very well, after a recombination, when neutral hydrogen is formed and the cosmic background is somewhat released or decoupled from matter, we have a few tens of million years, up to 50, 100 million years after the Big Bang, where the universe is mostly dark, mostly composed by neutral hydrogen. So these are called the so-called dark ages. Then 100 million years after the Big Bang, a few 100 million years, the first stars, first galaxies start to be formed. The ultraviolet photons start to ionize the universe, and then the universe start to becoming transparent. The intergalactic medium start to becoming transparent. First galaxies are evolving, and so on. So this is really a very interesting phase of the universe, which is subject of many investigation and still many open issues about actually the star formation rate evolution up to these very early epochs, the existence and properties of first population of stars, so-called pop-3 stars, the sources that cause the cosmic ionization and the evolution of cosmic ionization itself, and the properties of the bulk of the population of primordial galaxies, whose luminosity is expected to be below the detection threshold of even the largest and most sensitive facilities in the optical near infrared. Long gamma ray bursts are very promising tools from this point of view for shedding light on these open issues, again, because they are associated to star-forming regions, because they are produced by stars that explode where they were formed. As said, they can be detected up to the very early universe. So, as sketched here on the right, in the sketch on the right, they are bridging our knowledge of the universe from low redshift up to the very early epoch of the universe, the so-called cosmic dawn, again, when first stars, first galaxies were formed and the ionization started to take place. So just to give you an idea of the high power of gamma ray burst, what you see on the bottom left, is the image, the near-infrared image of the near-infrared afterglow following the highest redshift gamma ray burst that up to now. This is a redshift 9.2. So it is true that nowadays we have some bright galaxies detected, for instance, through the Hubble Space Telescope deep field at redshift higher than 6, 7, 8. So a redshift higher than 6 means the first billion of years of the universe, which is the epoch of the universe, which is subject of this very tough investigation. It is true the AWST is going to show us to unveil another fraction, substantial fraction of these primordial galaxies. But most of these galaxies are still the brightest galaxies. They are still detected, most of them, through gravitational lensing, thanks to galaxy clusters in the line of sight, magnifying the light emitted, the weak light emitted by these primordial galaxies. But instead, what you can see on the left is a direct detection of an emission following the explosion of a star. It's a way of detecting an exploding stars a few hundred million years after the Big Bang. So this is a power that only gamma-ray bursts can tell us. Gamma-ray bursts provide a direct detection of exploding stars in the very primordial universe. And as you can see on the right, this is the star formation rate evolution as a function of redshift, which is still subject of a large uncertainty at threshold 6 for the reasons that I already outlined, that only a few bright galaxies have been detected at this very high redshift. And from these galaxies, it has to be extrapolated the actual star formation rate. And the red crosses show the accuracies that you would obtain on the star formation rate evolution up to a redshift of 10 or even more, with a statistical sample of many tens of gamma-ray bursts at threshold 6. Of course, gamma-ray burst would also provide a direct route for directly detecting POP3 stars. This is another line of research, another channel of understanding of the problem of the universe that is completely possible only with gamma-ray burst, direct detection of the first population of stars. But even most impressive is that if you have a look here, on the top left, you have a sketch of the fading afterglow. So this is an image taken after 1 hour or just more than 1 hour, showing the afterglow, and then the afterglow fades away. And when the afterglow fades away, there is nothing. You can see nothing. So as you can see in these 6 images, which are 6 images taken by the Hubble Space Telescope in the direction of the 6 very high redshift gamma-ray bursts, as you can see, very high redshift gamma-ray burst, a few hundred million years after the Big Bang, you can see, even with the Hubble Space Telescope, nothing. So you know that in this direction, at this redshift, there are 6 very high redshift galaxies, only because we were capable to detect and localize the high redshift gamma-ray burst and to perform an efficient follow-up from the ground with robotic telescope, then with large telescope, catching this quickly fading near-infrared afterglow and doing absorption spectroscopy and hence the redshift of this emission and hence of the Ross galaxy. This means that gamma-ray bursts are providing with a unique way, a very powerful way of detecting, localizing, and measuring the redshift of galaxies that are so weak that would be undetectable, are undetectable by the Hubble Space Telescope, and of course at higher magnitudes. This will also be true in the JWST era. As I mentioned before, these very large sensitive and less sensitive infrared facilities will still detect the brightest fraction of primordial galaxies. Instead, with gamma-ray burst, we directly detect, localize, measure the redshift of galaxies that are invisible even to these large facilities. But moreover, of these invisible galaxies, if we are so efficient in the follow-up of the infrared afterglow before it fades away, and we can do a sensitive absorption spectroscopy of these invisible galaxies, we can also, as you can see in this spectrum on the bottom, study the metallicity, the neutral hydrogen fraction through the Lyman alpha absorption that is prominent here, and also the properties of the intergalactic medium. So gamma-ray bursts allow the detection, localization, identification of the bulk of the low luminosity, low mass luminosity primordial galaxies, and moreover, they also allow to characterize them, to measure their metallicity, the neutral hydrogen fraction, and also the evolution of the ionization, the properties of the intergalactic medium around them. So these are clearly breakthrough properties of gamma-ray bursts, very much complementary and additional to what will be done by JWST, SKA in the radio, for instance, or very large telescope like ELT, TMT in the next decade. This is very well known in cosmology. Here, the main issue is that despite already 25 years of efforts since we discovered the first redshift of gamma-ray burst, we are still stuck with only a few let's say less than 10 or more or less 8, 10 gamma ray bursts identified at redshift higher than 6. And this is due, of course, to the main limitation affecting current gamma ray burst detectors and the inefficiencies affecting the follow-up from the ground of this gamma ray burst. So not by chance, if we have a look at the main science case and scientific objectives of the future next generation gamma ray burst missions, which are being developed by the worldwide community in Europe, in the United States, in China, in Japan, and being proposed at several stages to the main space agencies, have probing the early universe with gamma ray burst as one of the main objectives. And of course, we know gamma ray bursts are also very much investigated for multi-messenger astrophysics, and more in general, these missions aim also at providing a strong contribution to time domain astronomy, and thus providing a very strong synergy with the very large facilities of the future in all the electromagnetic domain and the multi-messenger domain. Here I list some of these mission concepts that are among the most advanced ones. So Theseus in Europe, IZ Gundam in Japan, Gamma Explorer and TAP, Transient Astrophysics Probe in the United States. And I focus just, I say a few words about the Theseus mission concept, Transient Energy Sky and the Universe Surveyor, which is the European next generation gamma ray burst mission concept that was proposed to the European Space Agency in 2017 in response to the call for a next medium-sized mission to be launched in 2032. The consortium proposing this mission was coordinated by Italy, is still coordinated by Italy, because this mission was selected by ESA in 2018 for a 3-year phase A study. The phase A study was successful. Despite at the end ESA decided to select a mission to Venus, a completely different field of science, let's say, but still we are reproposing now this mission concept, which is the most advanced of this mission concept because it had 3 years of study by the European Space Agency for the next opportunity. We are just submitting in a few days, this week, the new proposal to the European Space Agency. So the concept of Theseus, which is the same, mostly the same as the other mission concept that I mentioned. So this is a concept that is in the mind of the worldwide community since many years. It's a kind of the dream of the gamma ray burst and multi-messenger, and time domain astrophysics in the world, and is to overcome the limitation, as I mentioned, of current facilities and the current observational process leading to the redshift measurement. First of all, expanding substantially the capability of gamma ray burst monitors with respect, for instance, to those on Swift, for those on Fermi, Conus Wind, and so on, which have a limited energy band, not optimized for high redshift gamma ray burst. So in the case of Theseus, this would be achieved by flanking, putting together 2 sets of different, let's say, all-sky X-ray gamma ray monitors, allowing to go to the soft X-rays, so to detect gamma ray burst also below a few keV with an unprecedented sensitivity and a locational accuracy of the order of the arc minutes. This will provide the substantial improvement in the detection rate of very redshift gamma ray burst, and of course will allow a mission like Theseus to detect and localize any class of gamma ray burst. So Maria Giovanna has just presented all the classes of gamma ray burst, and of course the group at ICRANet is working on all the different classes of gamma ray burst, and a mission like Theseus will be capable of detecting, localizing, and characterizing all of these classes. Moreover, as I said, we have to reduce the inefficiencies leading to the follow-up in the near infrared, and at the end to the measure of the redshift. So we have to identify that these gamma ray bursts are at high redshift. We need the measure of the redshift. We need the characterization, as I showed, the spectroscopy of the afterglow to characterize the Eros galaxy, this invisible galaxy. And this is done by putting directly on board the capability to the spacecraft of the follow-up in the near infrared. So not relying on robotic telescope and on the ground, but to include in the instrument suite of the mission near-infrared telescope, that for Theseus is a 70 centimeter class near-infrared telescope, coupled with the capability of the spacecraft to slew directly in a few minutes to point the direction, the infrared telescope to the direction of the gamma ray burst detected and localized by the monitors, in a way similar to what Swift is doing in the X-ray. So to give you a flavor of the capabilities of such a mission, this is the current situation with respect to our capability of detecting and identify high redshift, very redshift gamma ray burst. This is what the product of 20 years of observational efforts, as you can see, both on the left in a luminosity redshift diagram and on the right in a cosmic cone. You see that still, as I was mentioning, we have only a few gamma ray bursts detected and identified at redshift 2006, which means the first billion years of the universe. And instead, this is the red dots, what we would obtain with a machine like Theseus in only 3.5 years of operation, 3.5. So this is simply a nominal duration, because a mission like Theseus as Swift could last 10 years, 15 years. So it could really produce a huge sample of gamma ray bursts with measured redshift, and especially at redshift 2006, not only measured redshift, but also the full multi-wavelengths characterization. Of course, Theseus will also, the impact of Theseus, or a mission like Theseus on the early universe science, would also be in synergy with the very large facilities in the near infrared of the next decade. For instance, ELT, TMT, as I was mentioning, or even Athena in the X-rays, as is sketched here, with Theseus providing the targets for these facilities. So while Theseus provided detection, localization, and characterization and moderate resolution spectroscopy of this very redshift gamma ray burst, a follow-up within a few hours or one day also with the ELT, for instance, would provide the capability of fully characterizing the metallicity and neutrality fraction, or even imaging these very redshift galaxies. The same, of course, for JWST, if they could operate simultaneously. So to go directly to the impact on the early universe study, I already showed how a statistical sample of, let's say, 40, 50 gamma ray bursts at redshift 2006 detected and studied by Theseus would produce this level of accuracy, the red points, again here, on the star formation rate evolution at redshift 2006, which is still subject to large uncertainty. Well, it is true that JWST in the next year will reduce substantially this uncertainty, but still, as I was mentioning, it will miss the bulk of the population of very low mass, very low luminosity redshift galaxies. Only gamma ray burst can give us a direct access to this population. And this is showing how, as I was mentioning, instead, again, by providing this deep study of the primordial population of galaxy, Theseus will allow to solve, again, the uncertainty on the cutoff magnitude of the luminosity function of this primordial galaxy. This is the luminosity function as a function of redshift of primordial galaxy, and you can see in this sketch that we don't know where is the cutoff. And knowing where is the cutoff, there is a big question mark, is of paramount importance for understanding this galaxy formation, the first galaxy formation, but also to understand if the stars in these galaxies and the properties of these galaxies are such to allow the photons of first stars to reionize the universe. Because otherwise, the cosmic reionization remains a very big mystery. And this is still a big issue to be solved. And this is the accuracy, the red line, with which Theseus, with only a few tens of gamma ray bursts, but as I said, in a few years, it can also get 100 or more high redshift gamma ray bursts, the accuracy with which could measure the cutoff magnitude of the luminosity function of primordial galaxies. And this is another sketch showing in a more direct way the impact of the Theseus measurements, or a mission like Theseus, on the assessment of cosmic ionization. So as I mentioned, first the main hypothesis on cosmic ionization is that it was produced by the ultraviolet photons produced by the first population of stars. So we need to have enough stars at these very early epochs, and this is why star formation rate evolution is very important to be assessed. But we also need that these ultraviolet photons can escape the Eros galaxy and go into the intergalactic medium and reionize it. So a fundamental parameter is this one that you see in the x-axis, the FS, the escape fraction of ultraviolet photons from the Eros galaxy. Let's say on the y-axis, you see the density of ultraviolet photons. By combining the measurement by TCUs, you can constrain what is the reality. So the red line here separates two regions in the plane where the combination of ultraviolet photons density and escape fraction would allow or not stars to sustain cosmic ionization. So we did simulation on both hypotheses. On the left, the blue on the left is in the case that they are not sufficient. On the right is that they are sufficient. So TCUs would allow to disentangle this main issue in modern cosmology. And finally, this is also showing the capability of TCUs of extending the measurement of metallicity evolution up to the very early universe. So gray and red and blue dots are what we can obtain now with quasars and the current population of gamma ray bursts, and where red and green dots are what you could do with TCUs up to a ratio of 10 in two different hypotheses. You see, the red and the green dots refer to two different assumptions on the slope of the metallicity evolution. Okay, so now so there is of course a big interest in this use of gamma ray bursts for investigating the universe. But let me now shift to the other very intriguing and very promising way of exploiting gamma ray bursts for cosmology, which is, as I mentioned, using them for measuring cosmological parameters and ultimately investigating the cosmological constant, the dark energy, or alternative cosmological models. So big, again, and other big issues in modern science. So first of all, why we should investigate one more cosmological probe in this respect when we already have CMB, type-1a supernovae, baryonic acoustic oscillations, galaxy clusters. We are going to have Euclid and mission like Euclid exploiting the galaxy-galaxy distribution, redshift distortions. There are many methods at different level of accuracy or reliability. We have already many probes, as we know, all converging on the standard lambda CDM scenario, with a universe which is almost flat, where cold dark matter or dark matter dominates the matter component and the matter density energy component, and this cosmological constant of dark energy constituting the prime component of the universe, producing this expanded acceleration. Well, as you can see on the left in this omega m, omega lambda plane, omega m of course is represents the matter density, and lambda the cosmological constant of dark energy, if you wish, density. You see that different probes produce contours in different orientation, which means that each probe has a different sensitivity to different cosmological parameters because of their different redshift distribution and on the different methods in which they are used to extract cosmological information. So this is one reason. It is only combining the different probes that we can be quite sure of a given scenario. It is combining the CMB and type-1a supernovae that we are quite confident that the universe is almost flat and omega m is around 0.3. But there were, as you may know, debates also on how much significant is the evidence from type-1a supernovae that omega m is lower than 1 in a flat universe. And so adding clusters, adding other baryonic acoustic oscillations give us more confidence. So more probes, more confidence on the convergence on a given cosmological scenario. In addition, of course, each cosmological probe has its own systematics. Type Ia supernovae, most famous case, of course. They also they played a main role in assessing the cosmic acceleration. Of course, this is a Nobel Prize-winning discovery. But of course, as I mentioned, there were many debates on and if systematics, evolution effects. Here I list some possible effects affecting the way in which type Ia supernovae are standardized. So as we know, as you can see on the top right figure, type Ia supernovae are not standard candles. They are not by themselves. They can be standardized through a correlation between the peak magnitude of the supernova and the shape, or if you wish, the decay time of the light curve, which is sometimes called the Phillips relation. And as I will discuss, has already been anticipated in a way by Maria Giovanna, we are aiming for these reasons to exploit also gamma ray bursts for cosmology. But one main reason, I will get back to this in next slides, is that is the redshift distribution of gamma ray bursts. The fact that they can be detected up to a redshift of more than 9 would make them the cosmological probe in this respect with the highest redshift distribution compared to supernovae, type Ia supernovae, which arrive to 1.6, 1.7, or baryon acoustic oscillation, which you can use up to a redshift of 2 or 3, or the measurements that will be done by Euclid, again, up to a redshift of 2 or 3. AGNs are also being investigated as high redshift probes, up to a redshift of 5, 6. Here, gamma ray bursts easily go up to a redshift more than 9. So really a unique probe also in this respect. One of the most, or maybe up to now, the most investigated way of, let's say, standardizing gamma ray burst or extracting cosmological parameter information from gamma ray burst is based on this correlation between the spectral peak energy, as you can see on the left, and as you know very well, most of you, gamma ray burst spectra, when expressed in UF-nu, so the bottom panel of this figure, show typically a peak. So this is an average spectrum of gamma ray burst in the X gamma rays, the prompt emission of gamma ray burst. This is a typical spectral shape of a gamma ray burst. It is true that gamma ray bursts show a strong spectral evolution. It is true that there are sometimes extra components, power law, black body features, some deviations, but typically from 10 keV up to 1 or 2 MeV, the dominant component is this peaked shape, smooth broken power. And the characteristic feature of this spectrum is the spectral peak energy, EP, which is the photon energy at which the spectrum peaks. So it is simply a wavelength or a frequency. It's simply that in high energy astrophysics, we express the wavelength or frequency of the radiation in terms of the corresponding energy of the photons. So photon energy, if you wish, is the color of the gamma ray burst. And as you can see on the right, starting from 2002, 20 years ago, right 20 years ago, based on the first small sample of gamma ray burst, we measured the redshift coming from the Beppo-Sachs mission, which was the first mission capable of systematically accurately locating gamma ray burst and allowing the discovery of the afterglow emission in the X and in all the other wavelengths, and allowing the first redshift measurements of gamma ray burst. And one of the main discoveries is the discovery of this correlation between the spectral peak energy and the total radiated energy in the isotropic emission assumption, which is EISO. As you can see here, this is an updated sample. Now we have more than 200 gamma ray bursts that can be put in this plane. So more than 200 gamma ray bursts for which we have a redshift measurement and a good measurement of the spectrum. As you can see, all of them follow the correlation. So of course, this correlation is very much investigated also for its implication for the physics of the emission of the gamma ray burst. But here, let's focus on, and also for understanding different subclasses of gamma ray burst in a way similar to what Maria Giovanna explained for the fundamental plane with other observables of gamma ray burst. But here, let me focus on the use for cosmology. So we have a correlation between the spectral peak energy, which is simply unobservable. We measure the spectrum, we measure the spectral peak energy, we can transform the spectrum into the cosmological rest frame simply by multiplying, by scaling by 1 plus that. So the intrinsic spectral peak energy, so the photon energy at which the spectrum peaks in the cosmological rest frame of the gamma ray burst is simply the observed one multiplied by 1 plus theta, trivial. This observable correlates with the total radiated energy, which of course is computed or is linked to the measured fluence, the total flux integrated over the duration of the gamma ray burst, through the luminosity distance. Of course, this is also quite trivial, so it depends on the redshift and on the cosmological parameter and the cosmological model and parameter that you assume in the computation of the luminosity distance. So we have in principle a correlation that can allow us to standardize gamma ray burst. However, the main issue here is that different from type A supernovae, we don't have enough very low redshift gamma ray bursts. So almost all gamma ray bursts are at redshift higher than 0.05. The great majority is at redshift higher than 0.1. So we cannot calibrate this correlation in a cosmology independent way. So when we discover this correlation, and so the plots that you can see on the bottom left, the isotropic released energy or total luminosity of this gamma ray burst has been computed by assuming the standard cosmology, let's say. So how can now we use this correlation for measuring the cosmological parameter? Well, we can avoid, of course, this circularity problem by fitting simultaneously, if you wish, the cosmology and the correlation, which means in a very simple basic scenario, the exercise that we did in 2008 to actually assess if we can use this correlation for extracting cosmological parameters information. So what we did was to assume a lambda CDM cosmological model where, not a lambda CDM, a CDM cosmological model flat, because of course CMB combined to the prediction of inflation tell us that the universe is almost flat. So if we assume a flat CDM model, we can then ask us what happens to the goodness of fit of the correlation or the dispersion of the correlation as a function of the value of omega m, which is now the only free parameter in this assumption, that is assumed to compute the values of the EISO, the isotropic released energy, or the luminosity. So we assume omega m of 0, for instance, we compute the ISO for each gamma ray burst, we fit the correlation, we obtain a goodness of fit, we obtain a likelihood, a minus log likelihood, or like a square. We then assume omega m 0.1, 0.2, 0.3, 0.4, up to 1, and we compute each time the log likelihood or the chi-square. And what we found is that the minus log likelihood, so if you watch something equivalent, if you wish to the chi-square, even if this is a more complex likelihood needed to fit such a correlation, has a nice parabolic shape, minimizing right at omega m around 0.3. So if we, of course, integrate the likelihood and the probability density function, we can also quantify this result. And here you see what we could obtain with only 70 gamma ray bursts in 2008. And in a more recent work with more than 200 gamma ray bursts, you see that only with gamma ray burst, if the universe is flat, we have a direct evidence, a significant evidence that omega m is lower than 1 and is around 0.3. So if we didn't know anything about type A supernova or any other probe, we could do this in the 90s. If we could, yes. Unfortunately, there was not the possibility of localizing gamma ray burst and measuring the redshift in the 90s. But if you could do, you would have evidence only from gamma ray burst that the universe, if the universe is flat, as the CMB and the inflation converge, the omega m is lower, significantly lower than 1, is around 0.3, and the universe expansion is reaccelerating. So this shows that we can use this correlation to extract cosmological information or information on cosmological parameters from gamma ray bursts, and that gamma ray bursts by themselves independently provide one more evidence that omega m is around 0.3. And the universe is accelerating, so we are facing cosmological constant, dark energy, whatever you wish. We can also release the flat assumption, so we can let free to vary also omega lambda, the cosmological constant density or dark energy density, and you can see that the contours that you obtain with gamma ray burst, this is a quite old diagram, so this is many years ago, but already gamma ray burst produced a confidence contour which was comparable to the other main or more standard cosmological probes. Of course, you can also, so there are actually, despite the GRB community is still, let's say, skeptical, not so strong on this line of research. There are hundreds of papers published in PJ, Montinotti, so in the main journal worldwide, investigating the use of this correlation, and as I will mention, similar correlation for extracting cosmological parameters on gamma ray burst. And one of the most popular methods is to reinforce this method by calibrating gamma ray burst on type 1a supernovae. In the same way, type 1a supernovae are calibrated against C-phase. So you use C-phase to calibrate type 1a supernovae. You can use, if you believe in type 1a supernovae, so once you have demonstrated that as an autonomous independent probe, gamma ray burst can provide cosmological parameter information, they provide evidence that omega m is around 0.3 for a flat universe. You can also decide, okay, that you want to use gamma ray burst to extend the measurement double diagram that can be obtained with type 1a supernova or BAO and so on. And this is what is shown as examples in this slide. When many authors, here I showed just a couple of examples, use type 1a supernovae to calibrate gamma ray burst up to redshift 1.7, which is the higher redshift of type 1a supernovae, and then they fitted the correlation with this low redshift gamma ray burst, and then they could use the calibrated correlation to extend the Hubble diagram. So you see, for instance, especially in the bottom diagram, where black points are gamma ray burst, blue ones are type 1a supernovae, red points are baryonic acoustic oscillation. How much important is the use of gamma ray burst for extending the Hubble diagram up to very high redshift? This is very impressive. And of course, you can obtain much more accurate measurement of omega m and other cosmological parameters already now, thanks to this kind of calibration. As already mentioned by Maria Giovanna, but here I just go quickly because I focus on the peaky iso correlation. There are other correlations. Here is a list in this table of correlations that have been investigated for extracting cosmological information or standardizing gamma ray burst. They involve, for instance, instead of the total radiated energy, the peak luminosity, or they extend the peak ISO correlation with other observables, for instance, from the early afterglow, or as the correlation that was described by Maria Giovanna in the previous talk, they mostly based on early afterglow properties. So this is just a list. I don't have time, of course, to go through all of them, but this is to be taken into account. And of course, in addition to this, other groups of research are putting together gamma ray burst, for instance, with AGN, which is the other high redshift probe, even if not as high redshift as gamma ray burst. So putting together AGN and gamma ray burst. And this is an Hubble diagram that puts together gamma ray burst and AGN. Of course, the final aim of this research, once, as I mentioned, it is very important to get confirmation of a given cosmological scenario by different independent cosmological probes as we did. It is true that putting together these cosmological probes, as I mentioned, you get much more confidence on the paradigm, for instance, the standard paradigm now of an accelerated universe with omega m more or less of 3 and mostly flat universe. But if you want to go beyond, actually the final aim also with gamma ray burst is to provide clues to the investigation of the cosmological constant, the dark energy, or whatever is this main dark component of the universe, and this is a simple classical parameterization, the Chevalier-Polanski-Linder parameterization of dark energy, so which includes also evolutionary theme of dark energy, just to mention, or as I show, to investigate alternative explanations, so like modification to the equation of field, the equation of general relativity. And this again is to remark why gamma ray burst. According to the current understanding of cosmic evolution, the transition redshift, the epoch at which dark energy or the cosmological constant start to dominate the expansion of the universe and so produces this acceleration, is at redshift more or less 0.5. So why you need to go to high redshift of 8 or 9 is allowed? Well, it is very simple, as you can see on the bottom right. It's only fitting an Hubble diagram, modeling Hubble diagram extended to so high redshift that you can better discriminate different curvatures of the Hubble diagram at lower redshift. And this is these curvatures that contain the information on the dark energy and on its possible dark energy evolution. So it's like when you fit a spectrum, no? If you are an X-ray astronomer, if you fit a spectrum, or you take a spectrum of a gamma ray burst, you can say, okay, I need only a narrow energy band around the peak energy. Well, no, because if you don't have a broadband energy spectrum over several decades of energy, you will not be able to measure any feature in the spectrum with a good accuracy, even if the feature is in a given limited region of the spectrum. This is very well known. So you can see also in the top right, left, different cosmological model based on different predictions. So I just conclude. I think I am out of time. Again, I show the capability of emission light is used, substantial improvement of redshift measurement for gamma ray burst. So this mission will produce sample of hundreds of thousands of gamma ray burst measured redshift, especially at higher redshift. This mission will also provide an unprecedented characterization of the prompt emission. As I show on the top left, you can see the effective area, so the sensitivity of this use gamma ray imaging spectrometer compared to the other gamma ray burst monitors. As I mentioned, there is an unprecedented extension done to the soft X-rays. This means that, as is shown in this spectra, you can take the figure on the right, the bottom panel compared to the top panel. You see how much, what I was saying before, you need a very broad energy band for measuring the spectral gamma ray burst for correctly and accurately characterizing this prompt emission, the curvature, the spectral peak energy. So this mission will also produce a substantial improvement in the measurement of gamma ray burst with this correlation. And what I show here in the table are simulations. So current data we compare to a simulation with 500 gamma ray burst. It will also allow to calibrate in different way the correlation. So you would obtain very accurate measurements of omega m, but also accurate measurements, for instance, of the parameter of the equation of state of dark energy, as is shown in the last line of the table and on the bottom right figure, where in red you see the contour obtained with gamma ray burst added to other probes. So the addition of gamma ray burst would improve substantially our understanding of the evolution of dark energy. Okay, so here I skip. I would like just to conclude mentioning another very interesting feature of gamma ray burst. This is cosmology, but this is also fundamental physics. With gamma ray burst, especially with this future mission, we will get a huge sample of these cosmological sources, which have the ideal properties for testing the Lorentz invariance violation, which is predicted in different ways by different families of quantum gravity models. You know, of course, they predict that the speed of photons changes as a function of the photon energy. So to test this, we need, and of course, the net effect, the delay or the opposite effect, so the difference in time that you could measure your sensitivity, of course, depends on the redshift of the source. Higher the redshift, more sensitive you are. on the difference in energy of the photons, and so larger the difference and larger you are sensitive, and of course on the number of photons. And this is the ideal of gamma ray burst, which produce photons from a few keV up to several MeVs, or even more, of course. They can be detected at less than 9, and they produce huge amount of photons. So there is a lot of interest also in using gamma ray burst for testing Lorentz emission violation, and several exercises have already been done, putting some limits. So I'll leave you with this conclusion, and thank you very much for your attention.
Okay, thank you for the talk, and unfortunately we don't have time for the questions, so maybe we can discuss it later. Okay, we need to move on already with the 5 minutes delay. So yes. Thank you again,
thank
Professor
you.
AMATI. The next talk will be by Professor Ehud NAKAR. Okay, if you switch off your slides, Professor AMATI.
Yes.
Okay. Okay, let's check the microphone and the slides. Okay, we see your slides and the microphone.
Yes. Okay.
We see
there is time to intervene a second.
I think we can do it after this talk. There is a time break, so we can make it after. Okay.
Lorenzo, just one statement.
Yes, thank you, Remo. Yes.
We are obtaining interesting result of looking at the change of your relation also with Z.
Okay.
And we are fighting with time to be able to present some results by the last day of the meeting, but please stay online because I think they are very crucial. And also very crucial is to our understanding of Cocoon and the difference between the binary-driven model and the single-star model of traditional cosmology. And I think we have some important result, which will add to the presentation of NAKAR, which is following. Thank you.
Thank you, Remo. Yes, of course, absolutely. Thank you very much.
Thank you. Okay, the Professor NAKAR, the stage is yours. You can go ahead.
Can you hear me?
Yes.
Okay, so let's start. Hello, everybody. I would like to tell you today more about jets, cocoons, and shock breakout. I hope that I will cover everything that I planned. I'm not sure. We'll see how it goes. So this is basically the first part of the talk, which will take us about an hour and a half. So what is the outline? I will start with the physics of a jet propagation in dense medium. So in a sense, we can forget about everything except for a jet. We don't care how this jet is produced, and we don't care where it is. The only thing that we care about is that it's moving in some medium. And the question is, what is the physics of this process? And I will talk about it. You will see that during this jet propagation, there is a cocoon which is formed. We'll define what is a cocoon and how it is affecting the jet propagation. And later, we'll see what is the emission that is coming from this cocoon. Then we'll switch gears to something very different. We'll actually talk about what are radiation-mediated shocks. It will be an important piece of physics, which is important to understand what happens when the shock is breaking out. And having this, after understanding that, we'll discuss about the prediction for the emission of relativistic shock breakout. And finally, if we'll have time, we'll talk about what are the consequences, how this prediction is seen or might be seen in low luminosity gamma ray bursts. So let's start with jet propagation intensity. So we're having the following scenario. We have a jet. We launch it inside, in this case, a star. And I would like you to look at what happened when the jet propagates. Before I'm running this movie, I would just like to give credit to Or Gottlieb. He's now, he was a PhD student in my group. He's now a postdoc in Northwestern. You will see many results of different simulations. All the simulations that I will show here were done by Or. I personally do not know how to run a computer. So he deserves all the credit for the simulations. So now let's look, I'm starting the movie, and you see that the jet is launched. You can see how narrow is the jet. And just look at the movie. Okay, so I start the movie roughly at the point where the jet is going to break out from the star. And let's look at what we see here. This is the density. So you see this is a region with low density. This is actually the jet. If we say, for example, plot the density of the energy, you will see that most of the energy is actually along this jet. You see here that there is a shock. This is called the collimation shock. And you see that the jet is surrounded by material with a large gradient in the density. You see from very low density to very high density. This region is what we call the cocoon. And actually the pressure in this region, in the cocoon, is high, and we'll see that this pressure is affecting the propagation of the jet. And you will, and by another property is that you can see that the jet, which is launched conically, is actually propagating while attaining a cylindrical shape. And this is crucial for the jet to propagate in the star. If the jet was remaining conical, then the size of the jet would be something like here. This will be the jet will be roughly at this size. It will not be able to propagate through the star. It will need 3 or 4 times more orders of magnitude more energy to be able to break out of the star. We'll see what happens after the breakout. The jet is breaking out, and you see that all this material, which is very fast, is spilling out of the star. And you can see this, if we would run the simulation longer, you will see that the material, of course, is propagating almost the speed of light in this front. You see that the jet is not entirely stable. I will talk about that as well. And that's it, roughly. Are there any questions up to here? Okay, so let's try to understand the physics of what we've just seen and derive the equations that govern this propagation. I will just say before that, of course, what I've shown here is relevant both for long and for short GRBs. In long GRBs, the jet is propagating in a star, in the envelope of a star. In short GRBs, it's propagating in the ejecta from a binary neutron star merger. And the difference is that in long GRBs, the medium is static. In short GRBs, the medium is expanding. There is slightly different physics. I will not have time during this school to discuss the solution or the processes which are active when the medium is expanding. But there is a paper describing that, so you will be able to read about it if you're interested. So now let's talk about the structure of the jet. So what we have is the following. Let's concentrate first on what's happening in the left. A jet is launched here at the base. Material the material from the jet is going all the way up to the head. Okay, we'll talk about the shapes. That is what's happening here later. Now at the head, what we have, and we'll talk about it in more details in a second. We have a shock which is driven into the external medium, and a forward shock, and we have a reverse shock which is driven back into the jet. And the density and the pressure here is huge. So we have a region with very high pressure, and in the sides here, the pressure is much lower. So material is continuously if we sit in the frame of the head, material is going into the head, spills to the side. This is from the ambient medium. From the jet, goes into the head, spills to the side. So all the material from here is spilled to the side and forming here a region with a high pressure. Not as high as we have in the head, but certainly higher than we have at the base of the jet. Now, this material which is spilled sideways is forming this cocoon, which is engulfing the jet. So we have high pressure in the cocoon, and the jet which is launched here has low pressure. Now, region with high pressure and the region with low pressure, this is something which is unstable. So there must form here a shock. What happened with this shock is that this shock is slowing down the material which was launched in the jet, increasing the pressure in the jet. So we have here a region with a shock jet. This is the first time that the material launched by the jet is shocked. And the pressure in this region and in the cocoon must be uniform. So above this shock, which is called collimation shock, we have a uniform pressure in the jet and in the cocoon. Another property, which we'll discuss again later and see why it is so important, it is very important, is that in this part of the cocoon, we have material that came from the jet and spilled sideways. In the outer regions, we have material that came from the ambient medium spilled sideways. Now, the density of the material in the jet and the density in the material from the ambient medium is very different. The density in the jet is much lower than the density in the ambient medium. So we have two regions in the cocoon. One is called inner cocoon and the other is called outer cocoon. And there is a contact discontinuity between these two regions. We'll talk about that. Okay. In principle, there is also a possibility, that the pressure in the cocoon is not high enough to collimate the jet. So there is always a shock. But the question is whether the shock is strong enough to turn around and collimate the entire jet or not. So there are two different solutions for the propagation. One in jets are collimated and one in jets are uncollimated. Okay, we'll talk about that. So let's start with talking about what's happening in the jet, how we solve the evolution in the jet. So looking at the jet, at the head of the jet, we can move to the frame of the head of the jet. In the frame of the head of the jet, where the head is at rest, the condition is that the round pressure, which is basically the flux of momentum coming from the upstream, is equal to the flux of momentum coming from the downstream. This equation is equating the flux of the momentum. Okay, where the signs that you see here is the density, specific enthalpy, which is defined here. P is, of course, pressure, Lorentz factor of the jet, Lorentz factor of the head, velocity of the jet, velocity of the head. And this subscript A is for the ambient medium. Now, if the Lorentz factor of the jet is relativistic and beta jet is relativistic, even if not, then we can solve this equation and get the velocity of the head. And it turns out the velocity of the head depends on a dimensionless parameter, which is defined as L tilde, which is basically this ratio. We'll talk about this ratio in a minute. And if we know the value of L tilde, we know almost everything about the propagation of the jet. If L tilde is smaller than 1, the jet will be Newtonian, the head will be Newtonian. If L tilde is larger than 1, the head will be relativistic. Now you will see along this talk, I have many equations. I do not expect you to follow the equations during the talk. The reason that I put the equations here is that you will have them to, if you would like later, to go over the slides, and you will have everything concentrated in one place. So what I want you to follow is the rationale of what we are doing and the physics behind each equation. You really do not need to follow, and practically it's impossible. I cannot follow my own equations when we cover them so quickly. So the take-home message from this slide is that the head velocity is determined by the frame at which the momentum, the flux momentum from the jet and from the ambient medium are equal. Now, I want you to understand a very important point here is that the head can be Newtonian even when the jet is relativistic. So we launch relativistic outflow, but the head is propagating at a Newtonian velocity. And we'll see that actually in most cases, the head is Newtonian and not relativistic. So all the energy which we launch is going through the head and spilled into the cocoon. So the engine drives into this jet is basically lost up to the point that the jet is breaking up. So let's say a few words about what is this L tilde. This equation for L tilde can be written like that. What we assumed here is that the material is relativistic and that the jet is cold when it is launched. And you see that this is basically the ratio Lj, this is the luminosity of the jet, divided by the cross-section of the jet. This is the luminosity per unit area as measured in the rest frame of the jet. Rho A multiplied by C cubed, this is the energy, the luminosity per unit of area as measured in the jet frame. So the ratio of these two qualities, the energy luminosity per unit area in the ambient medium frame, divided by the energy per unit area of the ambient medium in the jet frame, this is what we call L tilde. If it's much larger than 1, then the head is relativistic. If it's much smaller than 1, then the head is Newtonian. And basically, the entire system is determined by 2 parameters. This L tilde, which is dimensionless, and the opening angle of the jet, which is again dimensionless. Now, after understanding the propagation of the head, there is another ingredient which we need to understand, and this is what is the physics of this collimation shock. Now, as I said before, we know that the pressure in the cocoon and the pressure in the shock jet are the same. And by the way, we can understand that this pressure can be the same in a very simple way. So we have material which is moving relativistically towards the top, and we have material which is at rest. Now, one can say, well, this material is moving relativistically. How do I know that the pressure must be the same? In order to see that the pressure must be the same, you can understand that we can always change our rest frame. We can go to the rest frame of the jet. In the rest frame of the jet, the ambient medium is moving relativistically downwards. So basically, there is no difference. If the pressure here was larger than that, and this will be the equilibrium, and pressure is, of course, always defined in the rest frame of the fluid, then we can go to the frame of the jet, and then we'll see that we need the pressure to be higher on the ambient medium than the jet, and this cannot work. So the only way to have an equilibrium here is that the pressure is equal, is the same. Now, we have here material with no pressure, here material with pressure. This implies that we need to have a shock, sorry, because if the pressure here is very low, then the velocity of sound is very low, is too low. And the shock will be what we call an oblique shock. So there is some change in the direction of the velocity, and this change is enough to increase the pressure in the shock medium here, in the shock jet. So we need to write the equations, and I will not write the equations here. You can find it in Bromberg et al. 2011, but we write the equations for the pressure in the shock medium as a function of this angle here. And this gives us the structure of this shock. Okay, so once we have the structure of the collimation shock, we can find the height of the collimation shock, where the collimation shock is, we call this region here Z hat. So the point of the collimation shock intersects the axis, the symmetry axis. And basically we have two possibilities. If the intersection takes place before the location of the head, so the head, let's say that the head is up here and the intersection is here, then we know that the jet is collimated. If the head is here and the intersection should have taken place here, then the head is not collimated. Okay, and here you can see this is an equation for the location of the head, very simple. And you can see that this intersection depends on pressure in the cocoon. Now you see that if we have the intersection location, then we know what is also the cross section, because if we know what is this place, we know what is this size here. And if we know this size, then we know the intersection of the jet. Okay, so we have also an equation for the intersection of the jet. If we have an intersection for the pressure for the size of the jet, then we can also have an equation for the size of the cocoon, and we have the size of the cocoon, we have the pressure in the cocoon. So you see that in principle, in order to solve the system, we need to solve everything simultaneously. We need the jet cross section to know the head velocity. We need the head velocity to know the cocoon volume. We need the cocoon volume to know the cocoon pressure. I remind you that the energy in the cocoon is basically all the energy that was launched into the jet and crossed the reverse shock in the jet. So once we know the jet location, we know the pressure in the cocoon, and we know the energy in the cocoon, we know the volume of the cocoon, so we know the pressure. And we need the pressure to know the jet cross section. So all these should be solved simultaneously. And this was done in Bromberg 2011. Any questions? Okay.
I think we follow this beautiful presentation, and it's very helpful. And first of all, I congratulate both you and your collaborator for the very nice images. And of course, one of the issues we are mostly interested in our approach is to justify the origin of the jet. But just to have an order of magnitude, I understand you will go more and more in detail with the head velocity, the cocoon, the jet, and the volume. But can you indicate what is the characteristic Lorentz gamma factor of the jet that you are envisaging? Without spoiling, I think all this will come from the observation and the detail of the model, but just an order of magnitude.
So everything that I described so far is independent of the Lorentz factor of the jet if the Lorentz factor is larger than 1 over the opening angle. If the Lorentz factor is smaller than 1 over the opening angle, then all the equations that I've shown needed to be revised. If the Lorentz factor is higher than 1 over the opening angle, then these equations are valid. So as far as the sensitivity of the propagation of the jet to the initial Lorentz factor is relatively low. If we measure, for example, that the opening angle of jets is of the order of 0.1 radian or maybe 0.05, so for this picture to be correct, we need the Lorentz factor to be larger than about 20. But we do not care if it's 20 or 100 or 100,000. Of course, we have other indications that it should be larger than about 100 or maybe 300, but not directly from considerations that are related to the jet propagation.
Yes, you made a very good answer, and we look forward. We agree on what you said, but let's wait for more detail. You will continue now, or you will continue in the next lecture?
No, I'll continue now. I have, I think, 20 more minutes or something like that.
Good.
Yes,
and then
you have 25 minutes.
25 minutes, okay. Now, I will not go through the derivation, but in principle, one can find the criterion, as I told you, the entire evolution depends only on L tilde and the opening angle of the jet. Theta naught is denoted here. So if L tilde is smaller than theta naught to the -4/3, then the jet is collimated. If it's larger than that, then the jet is uncollimated. Now, I remind you, theta naught is much smaller than 1. This is the opening angle of the jet. And again, we assume, of course, that the jet is ultra-relativistic and the theta naught is much smaller than 1. These are, again, conditions that goes into all this derivation. So whenever the head is Newtonian, so L tilde is smaller than 1, then it's also collimated. So all the Newtonian heads are collimated. Some of the relativistic heads are not collimated and some are collimated. And in principle, you can see all the different regimes. I will not go through all the different regimes, and I will not explain all the different notations here. But in principle, you can go to Bromberg et al. And find all the values of all the parameters, the velocity of the head, the volume of the cocoon, the height of the collimation shock, all the parameters which are indicating, which are explaining the structure of the system and how it evolved with time, as a function of basically the L tilde and the opening angle of the head. I will just say one assumption that we made. I will go back here. One assumption that we made when deriving these equations is that the pressure in the cocoon is constant, not only along the interface between the shock jet and the cocoon, but also between the base of the cocoon and the head. If the pressure here, if there is a gradient of pressure, let's say the pressure at the bottom is larger than the pressure at the top, then the shock jet will not be cylindrical. So will be some, the pressure here will adjust itself and the jet will become slightly less collimated. And we verified everything that I told you now, we verified by numerical simulations. You can see, for example, in all these numerical simulations, the jet itself is roughly cylindrical, and we also verified the pressure directly. And it is roughly constant. Now, this is an analytic solution for the head velocity. And one interesting thing that you can see is that when the density of the medium is a power law with a power law index alpha, then the solution is also, of course, a power law. And alpha equal to 2 is a unique case where the velocity is constant with time, and basically the structure of the head of the entire system is self-similar. Alpha smaller than 2, like that, the head is decelerating. Alpha larger than 2, the head is accelerating. You can see that also the shape of the cocoon is changing between the different regimes. In stellar envelopes, alpha is somewhere between 2 and 3. So we are somewhere between this solution and this solution. By the way, I would just say that everything that I described here is applicable for alpha as large as 5. So every alpha which is smaller than 5, you can use these equations. In Bromberg et al., we thought actually that this is alpha smaller than 3. Later, we found out that up to alpha larger than 5, the solution is viable. We have a recent paper from 2000, and actually it's still in the referring process, where we extend the theory to alpha of 5 and calibrate it numerically. So what is application to gamma ray bursts? We can take just the equations that I derived before. These equations are assuming a Newtonian head. So we need to write this equation, see if the head is indeed Newtonian, and if it is, then these equations are applicable. And if we put in what we expect are the parameters for gamma ray burst, so the luminosity of the jet is about 10 to 50 ergs per second. The duration of propagation is about 10 seconds. The density in the envelope is about 10 grams per centimeter square. The opening angle is about 10 degrees. We get a velocity which is about 0.25 c. So it's still Newtonian, but it starts becoming almost mildly relativistic. So we see that in typical long GRBs, we expect head velocities which range between about 0.5 for the weaker jets or more dense envelopes, up to about 0.5, maybe 0.6 for heads for jets which are extremely energetic. This luminosity, by the way, is not isotropic equivalent. Yes, this is a total luminosity in the jet. Isotropic equivalent in this with this opening angle will be about slightly more than 10 to the 52 Hertz. It will be about 2 times 10 to the 52 Hertz. So no, it will be about 10 to the 52 Hertz. And the value that you see here for the breakout time, for example, is a function of the radius of the stars for 10 to the 11 centimeter and 10 solar masses are calibrated numerically. So there is a paper that we wrote in 2018 where we checked all the equations in Bromberg et al. And found numerical calibration coefficients. And you see that roughly 15 seconds, this is the time for the jet to break out. And in the talk by Tzvi Tiran tomorrow, you will see how this time is relevant for the observation. And you will see that we actually have an observational evidence supporting that the breakout time of the jet, the time it takes the jet to go through the star, is roughly 10 seconds. Okay. And what we will show tomorrow, and I will just give you a teaser, is that the duration of this is, of course, what you see here is a duration distribution, how many bursts as a function of duration with the famous Covalier 93 plot. And you see that there are two typical timescales here, one which is roughly of the order of tens of seconds, and one which is roughly of the order of half of a second. Correcting this to the rest frame, it will be of the order of 10 seconds. And this peak here is actually reflecting the breakout time, but this we will show tomorrow. Again, this is a good place to stop for questions. Now I'm going to dive more into the details of what happens during the jet propagation. Okay. So I remind you, let's go back here. You remember that I said that you can see, where is it? Okay, it was during when we looked at them. Sorry if I'm going so fast back and forth. I wanted to show you again through the movie. Look at the jet and see that the jet here is becoming unstable. You see it's stable in this region, but it's becoming unstable and less stable. And you can see that this instability persists also after the breakout, not only before the breakout, also after the breakout. So let's talk for a second about this instability. So what you see here, this is a jet which is propagating. And I would say one thing I didn't say at the beginning, everything that I've shown you so far is for hydrodynamic jet with no magnetic field. I will talk about magnetic fields in a second. Now, here you see the energy density in the jet. You can see here, so it's a flux, yes, it's energy density. It's very high here at the beginning. It's becoming lower and lower because the energy from the jet is spreading. So the energy density is becoming smaller. Then it crosses the collimation shock. Again, the energy density becomes much larger. And you can see that here then the jet is becoming slightly wider because of this instability, and the energy density goes down. If you look, this is the energy per baryon. So this is basically what is the level of mixing in the jet. You see there is no mixing at the base, and as the instability grows, you see that in principle more and more mixing, there is more and more mixing of material from this is the inner cocoon, and this is the jet. So this is the interface between the inner cocoon and the jet, and you see this interface become unstable, and there is mixing. Here you see cuts, horizontal cuts. So you, for example, you see this location looking from the top, okay, looking from here, from the top, and you see this is the cut, and you see this is the unshocked jet. This red region here, this is this very narrow region here, and everything, and this region, this blue region here, this is the inner cocoon, and this region here, this is the outer cocoon. Okay, the energy density here is higher because of the high rest mass energy density. And you see, as we propagate to the left, the cuts, the second, this one is this one is this cut, and so on and so forth. And you see that there is an instability here. Does anyone have a guess what type of instability this is? Does it remind you any type of instability?
Is it kind of a diffusion?
No, this is a Rayleigh-Taylor instability. Okay? This is a Rayleigh-Taylor instability, and the reason for this Rayleigh-Taylor instability, I remind you, Rayleigh-Taylor is instability when you have two fluids, one on the top of the other, when there is a different densities for these two fluids. And for example, if you take a heavy fluid on light fluid, and you put it in the gravity field of Earth, so gravity is going downwards, it will become unstable, and you will start seeing like not exactly mushrooms, but yeah, it's almost like a mushroom, which are growing, which are fingers is a better description. You will see fingers go from the lighter fluid into the denser fluid, and vice versa, until they will flip, and the lighter fluid will be on the denser fluid as it in a stable configuration.
May I ask a question?
Yes.
This initial condition in the bottom, why this jet has this shape? Is the initial condition you impose, or?
The jet is launched with a conical shape.
Ah, okay.
Yes, we launch it in this way. We launch a conical jet.
Okay.
Okay. But the jet must be conical if it is a jet, because
yes,
the energy density in the jet might have a structure, if this is what you mean. But after the jet is launched and collimated at the base, as it propagating farther from the launching location, it will all the jet elements will stream along a streamline, and this will be conical. Okay.
Okay, thank you.
And the reason for this instability is the fact that we have you see that the material here is moving, is actually accelerating along this line. If you're following a streamline, it is shocked over here, and then it is curved in this direction. So if we have a curve, we have an acceleration, and acceleration is like gravity. And it turns out that this acceleration is becoming unstable in this route. So what you see here is basically Rayleigh-Taylor instability. After this location, there is another instability which kicks in. It's called Richter-Meshkov. I will not get into these details. But altogether, we have an unstable structure. And you can see that this instability affects very strongly various properties of the jet. Now, these instabilities cannot be seen in 2D. I will go back to the 2D. You see in 2D, everything is stable. All is good. So until a few years ago, all the simulation were in 2D, and then this instability was not shown. The first one, I think, to show this instability was Matsumoto about a decade ago, slightly less than a decade ago. And we also find it in all our simulations. Now, this instability instabilities have three effects, which I would like to discuss. First, it increases the jet head cross-section. You see that the jet head here is smaller, the cross-section here is smaller, here it's larger. So slowing down the jet a bit by some constant factor. It's not something which is affecting very strongly everything that I told you about the theory that we developed before. It's changing the numerical coefficient for this jet, which is moving slightly more slowly, and the numerical calibration that we did was including these instabilities in a hydrodynamic jet. Second, as you see here, it's initiating variability into the jet. So the jet is launched without any variability. The jet here is uniform, constant in time, but it gets out of the star with very high variability. So this is just to show you that in principle, in GRBs, we see very high variability. This variability can be induced by the propagation in the medium without having, even if the jet is completely constant in time. I do not say that it is, okay? I do expect variability in the jet, but some or maybe most of the variability that we observe may be a propagation effect. And finally, you can see that there is some angular structure which is induced by these instabilities. So even though the jet is launched at the base as a top hat, namely there is a uniform energy per unit of area at the base, and when we launch the jet, and no energy above some angle. This is what we call a top hat jet. So although the jet is uniform at the launching site, it is not uniform when it gets out also in the angular direction, not only in the radial direction. So let me say a few words about it really shortly because I don't have much time and I have many more things to say. What you see here again, this is another plot. Eta is the baryonic mixing. So the jet is launched with energy per baryon of 500. So if the jet would have been propagating in vacuum, the final Lorentz factor would have been 500. And what you see is if you go along this axis, what you see here at the bottom is what is the amount of baryon loading. And you can see that the jet, when it's breaking out, and you see this is long after breakout of the star. This is the radius of the star. So this is roughly the location of the collimation choke when the jet head is here. And you can see that there is some episode at the beginning where this is related to the time that the jet was still propagating inside the star. Here the mixing is relatively high, but after a short episode, the mixings become roughly constant. And you see that it's give you high variability. So for example, this red region is accelerating to a Lorentz factor of 500. This yellow region is accelerating to a Lorentz factor of say 80. So and this will induce later, for example, internal shocks. And it's also affecting strongly the efficiency of photospheric emission. So this induced variability must have a direct implication for the variability of mass is too strong, but it's almost certain to have an effect on the variabilities that we observe in the prompt emission. So this is one effect. Again, there are several papers discussing that I will not have time to get into. I apologize. The second thing is the structure that one obtains in the jet in the radial direction. So what you see here in this figure is this is the angle with respect to the axis. This is the energy as a per unit of solid angle, or what we call E-iso, in the jet after it's breaking out and going away. So this is in the coasting phase, long after it went out of the star. And I remind you that we launched a jet where there was a constant energy per unit of solid angle, and then it went to zero. above the angle that we launched, which is roughly theta j. You see that after the propagation in the star and the instabilities in the star, we have a very long region with a power law structure. So the energy goes down as a power law. This region above, up from here, this is the region coming from the cocoon. So if I go back, well, I will go back. If I go back, say to, I will show it later in a following slide, I hope. Following slide, no, so I'm sorry, I'm going back to, I needed to put more slides of what happens. Okay, let's go here. Okay, so this is a jet. This region. The region, you see this region here? This region here is an interface between the jet and the cocoon. This is what is affected strongly by the mixing. And no, this is not what I wanted again. Sorry. All this region here, this is the cocoon itself. So if I go back to where I was, and I apologize again for going back and forth. We have the jet, we have the region of the interface, where the energy goes down like a power law, and we have the region of the cocoon at very high angles. Okay, this is roughly half a radian, this region. You see the angle here is normalized by the opening angle of the jet. You see this is the energy, this is the Lorentz factor at infinity. So you see that the Lorentz factor in this region is larger than 100. This is of course related to the energy that we launch, we put by hand, roughly, so for the Lorentz factor that we launch, and this is something that we put by hand. The different figures here are unimportant, these are different models at different time. In all of them, you see a maximal Lorentz factor, which is at the center, and then the Lorentz factor goes down with angle all the way to sub-relativistic velocities at angle, which is roughly 5 times the angle of the jet. Now, the last thing that I would like to talk about today, do I have 4 minutes?
Yes, I have 4 minutes. You have a few minutes.
So the last thing that I would like to say is that this instability and the propagation of the jet is also affected by the magnetic field. So I described you so far hydrodynamic jet. You can tell me, why do we care? There is a chance that the jet is launched hydrodynamically by neutrinos and annihilation. It's possible. It's not the most favorite model. Most people think that the jet is launched actually via a blunt force Nike mechanism, and when in the launching, it's extremely highly magnetized. Now, one important thing to know is that we do not know what happens to the magnetization during the propagation. There are suggestions, / indication, / plausibility that actually there is a collimation shock also in ultramagnetized jet, and we know that there are. And in this collimation, not exactly shock, but a collimation structure. In this collimation, there is a nozzle, and in this nozzle, the jet is becoming unstable to king instability. And this instability is actually facilitating a very strong dissipation of the jet. And what we mostly care about is what is the magnetization level near the head. This is what's mostly important. And it's possible, even likely, some will argue, that even if the jet is launched ultra-magnetized, then during the propagation it's becoming mildly magnetized. Mildly magnetized is when the magnetic field energy and the baryonic mass energy are comparable. So sigma is roughly 1. It might be becoming even weaker than 1. So what you see here, these are different simulations with, these are magnetized, hydrodynamical jets. These are weakly magnetized with sigma of 0.1, and this is more magnetized, this is 0.0 and this is 0.1. And you see that the jet is becoming more and more stable. You can see here, these are the cross sections in this direction. The reason for this stabilization by the magnetic fields is that you can think about the magnetic lines that are in the jet like strings that actually enforcing the jet and making it harder to develop the Rayleigh-Taylor instability. And it is well known. It is also well known that when you just take two fluids, magnetized fluids, and one of the fluids have magnetic fields in both directions, like a grid of magnetic fields, then it is stabilizing against Rayleigh-Taylor instability. So it is still unstable, but much more stable. So magnetized jet, the effect of magnetized jet, of magnetization, will be to reduce the induced variability, to make, if we look at the structure of the jet, it will basically make this region to go down much faster. So this region will go down, the energy will go down much more sharply next to the after the edge of the jet. And that's it, more or less. The only one thing that I would like you also to think about before tomorrow is the jet is not always escaping from the star. It can also be choked, and it's most likely choked in many cases. I guess we'll talk about it as well. So just look what happened when a choke jet is propagated. So this is a jet. You do not see the star because this is showing motion, and the star is not. Now you see here, we stop at this location. We stop launching the jet, okay? So we do it slowly. The jet is launched, and here it stopped. You see that at some point, all the jet material is going through the reverse shock, and all we left is the cocoon, okay? And you will see that the cocoon continues to propagate. At some point, you will see the edge of the star because of numerical artifacts. You see this is the edge of the star. And you see that the cocoon continues to propagate, and it's still highly aspherical. And you will see it's getting to the edge of the star, and even so, the jet was choked relatively deep in the star, roughly 25%. Still, the cocoon is breaking out, spreading sideways, producing something which is very, very different than a spherical explosion. So I will leave you here, and tomorrow, at least the first part of the talk will be devoted to the cocoon. So we'll talk more about the cocoon and about the emission of the cocoon. Today we talked about the jet. Tomorrow we'll talk about the cocoon. So thank you very much. And
okay, thank you.
Questions.
Thank you. If you have a question, by the way, I want to say that we have a 10 minutes break now, and we will continue after. Okay, so Jorge, go ahead.
Thank you. I would like to know what is the composition and the equation of state of the jet, and if there is any injection of energy at the base. Thank you.
So the jet here is we do not care about the composition, because even all this physics, well, we almost don't care about the composition. All this physics is independent of the do you mean composition by what are the elements, or composition in terms of magnetic field?
What is the composition of matter? You have electron, positron, neutrinos. What do you have there?
We don't care. So neutrinos are unimportant. We are not getting to the neutrinos will escape from the system. The temperatures are not high enough to generate neutrinos, so we do not care. The physics of the hydrophysics of everything that I told you now is also independent of the composition. We don't care. This is a fluid. All we care about that we can use the baryons and electrons and positrons in the jet as fluids, and everything will work. The only place where the composition is important is in the structure of the shock itself, and this will affect, for example, the shock breakout and emission. But other than that, it is not very important. Now, I will tell you one thing. The star, of course, is composed of baryonic matter, regular baryonic matter, and the mixing in the cocoon is the properties of the cocoon are dominated by this mixing. So also the cocoon will always be dominated, at least in energy per baryon, it will be dominated by baryons, or energy per particle, it will be dominated by baryons. For the jet, everything that I told you will be the same. independent of the composition. As for whether energy is launched continuously into the jet or not, so in all the simulations that I've shown you here, the energy was launched continuously up to some point. If the jet already broke out of the stars, then okay, everything that breaks out continues, and when you stop the jet, you just stop the jet. If it is not, then you have the scenarios that I just plotted here. You have a choke jet. If the jet is not uniform, the luminosity is not constant in time, if it's variable, it will have significant implications. I do not have time to discuss variable jets. There is a list of papers. We wrote 3 or 4 different papers, or maybe 2, I don't remember, about 2 to 4 different papers about intermittent jets. And actually we show that if the jet is hydrodynamic, then we cannot generate GRBs with intermittent jets. If the jet is widely magnetized, we can actually do it quite nicely. So our conclusion in following all these works is that mildly magnetized intermittently launched jets, or we have an engine which is becoming stronger and weaker, stronger and weaker, stronger and weaker. If the change is 10%, we do not care. But if the change is, say, 90%, we do care. And then actually mildly magnetized intermittent jets are quite good candidates for to produce jets which are consistent with the observation of GRBs, at least long ones. I hope I answered the questions.
Hello, can I have questions? Fine, thank you. Hello, can I have questions?
Yes, go ahead.
What's a key parameter or characteristic or quantity which characterize the jet and jet spreading? Means
which parameter is?
Yeah, which quantities? Because either you have a jet isosymmetry, okay, and then you have jet braiding, which approach the spheric one. So what's the key quantity which you use to describe this, and what dynamic depends on which quantity dynamically you depend to have this picture? Means very thin nano jet. Okay, and then a spreading jet like around one is on the screen.
I'm not sure that I will try to understand.
You know, you have 2 pictures. Okay, one is very thin jet, very jet.
You're talking about what happens here?
The one on the screen. The other is very spreading.
Okay, so the difference between the one on the screen and the previous one is whether the jet is breaking out or choked. So I will show it again. You see that the jet is propagating. It's very thin, very thin, very thin, okay? Just like before. At this point, we stop injecting energy into the jet. Now, here we have relativistic material propagating towards the top. Here, there is a Newtonian shock. So if I stop injecting energy at the base, all this material will go through the shock and go sideways to the cocoon. See how it happens. Okay, that's it. We stopped. There is no more relativistic material. Now you have here high pressurized material moving. Everything here is Newtonian, or yes, every so the energy per baryon in the inner region is about 2 or 3. So this is mildly relativistic, and in the outer part here and here, the energy per the velocity of the baryons is roughly 0.1 c. And then this is not going to remain narrowly collimated. This region is going this is starting to spread sideways because it's Newtonian. And you see that it's becoming larger and larger.
Is it by diffusion or what? I just want to see why is spread it. No, why spread? Which quantity it what's the dynamic make a transverse motion?
Okay, there is always a transverse motion. Okay. Also, when the jet is propagating, there is a transverse motion, and the velocity of the transverse motion is roughly constant in both cases. The difference here is that when the jet was operational, the head moved much faster. Here I just don't have enough time, but also here you see that the jet...
By collision and diffusion?
It's shocks, it's not collision and diffusion, this is just shocks. High pressure, low pressure. We have here high pressure, we have here low pressure material with sound speed which is very low. You have a shock moving in this direction, that's it. You have here fast, take two fluids. One fluid with very high pressure, another fluid which is at rest and pressure much and sound speed which is much weaker than the sound speed, much smaller than sound speed in this fluid, will have a shock. Just like a regular Riemann shock fluid, that's it. High pressure, low pressure, you have a shock moving in this direction, that's it.
Yes, Rudy, I think that is very clear. What it can be helpful at the next lecture, you mentioned some Japanese contribution. Could you give us at the beginning of next lecture a complete set, as complete as possible, of reference, especially the one of your group and the different publication and the reference of the material you are presenting, which we can quote in our papers? Sure. This will be very helpful.
I will write a large. I will give you tomorrow.
Yes.
many papers, not only ours. There
Yes.
are many people who work on it, not only us.
Exactly. That will be very helpful.
Okay, I will do that.
Thanks a lot for this very interesting lecture.
Thank you for having me, for inviting me.
Thank you again. Now we have a break. Now it's still 10 minutes, so we will start with some small delay. Okay, 10 minutes, so it's 11:45 sharp Rome time. Thank you. Okay, I think we can continue the morning session after the break we have. So the next speaker is Professor Gregory VERESHCHAGIN. Gregory, do you hear me?
Yes, I can hear you.
Okay.
So, can you hear me? Yes.
Yes.
Okay, let me share the screen. Okay. Does it work?
Okay, we see your screen and the mouse cursor. So.
Okay, let me put maybe full screen. Is okay?
Yes. Okay. So the next speaker is the Gregory VERESHCHAGIN of the ICRANet. And the stage is yours. And I remind that the recordings are available on the YouTube, so you can also watch it later. Okay, so.
Okay, thank you very much, Giovanna. I think it was really nice to have Ehud's talk just before mine, because he actually introduced all the necessity. I don't need to spend time on explaining what is the cocoon and why it is related to relativistic jets. I will talk essentially on the observational appearance of these objects, and of course Ehud will talk about this himself tomorrow, so I think our talks will be correlated, but I will essentially concentrate on theoretical aspects of the photospheric emission, which is a narrow topic compared to more wide topic of general observational effects of cocoons. So let me start. The introduction will be quite short, therefore I will describe then hydrodynamic model, which is a very simple model and it's based on all the calculations which will follow. Then we'll basically talk about photospheric emission and the difference between so-called photon thick and photon thin outflows. And this terminology will be introduced.
Then I will talk shortly on dynamics and the propagation of the photosphere, essentially, because this is not a static object, and its geometry. And the rest of my talk will be focused on a particular case of radiation which happens in diffusive regime. I will also describe some case studies of gamma ray bursts with an emission which can be interpreted in this model and conclude. Let me tell you in few words what this work is based on. So the first really important contribution in this field has been the work of Abramovich, Novikov, and Paczynski in 1991, who realized that the photosphere of relativistic outflow is very different from traditional static photospheres. And it appears differently, its emission is different, and everything is related to the mean-free path of the photon propagating in expanding medium, relativistic and expanding medium. After that, there has been a lot of works using this fundamental contribution, which actually focused on some but not all possible cases which result from the appearance of this relativistic photosphere. And in particular, our work almost 10 years ago focused on a general description of photospheric emission in all possible asymptotic cases which follow from this treatment. This is from the theoretical point of view. From observation point of view, it's a very clear fact that there must be thermal emission trapped in the sources of gamma ray burst. This comes from the simple argument that the energy of the gamma ray burst can reach up to 10 to 54 erg. I talked about isotropic energy, and the variability time scale can be as short as 10 milliseconds. And just this fact is used in most of the works, in particular in the review of Zwiger 99, to point out that observed non-thermal emission must be originated at relatively large radii from the source, even if the source itself could be relatively compact with the characteristic times, crossing times given by this variability time. And nevertheless, from the same argument, it follows that there must be a huge amount of thermal radiation trapped in relativistic and expanding plasma, which could potentially be observed later on. The next point, I will come back to this point later on. The next point is that we did the particular analysis of several gamma ray bursts with thermal emission detected in the early afterglows of these gamma ray bursts 2 years ago, and these observations were crucial to determine one of the regimes of the relativistic photosphere not previously observed, namely the diffusive photosphere. So I will spend only a few words to mark the key development in observation and theory of gamma ray burst related to the photospheric emission. First of all, of course, with the launch of the Fermi satellite, we finally get quite a wide range of energy observable for each gamma ray burst. And this allows to see multiple components and confirm the presence of multiple components in the observed spectra in prompt radiation, but also in the afterglow eventually. And many cases with possibly thermal component in the prompt emission were detected. Particularly relevant was the burst in 2009 with practically completely thermal spectrum, but that was an exception. More realistic statement would be to say that when we have quite a good resolution of the energy spectra, suitable to make detailed spectral analysis, time result spectral analysis, practically in all cases, a thermal component can be detected in the prompt spectra of gamma ray burst. But also, it's important to say that in addition to these thermal components in the prompt spectra, there has been determined thermal emission in the early afterglow. Early afterglow usually is the moment in the light curve of the spectra when the thermal emission, the prompt emission is basically achieved. There is a strong fading out of the emission, and during this strong fading out of the emission, sometimes thermal emission is also detected in the spectra. Let me now introduce the hydrodynamic model that is used in this analysis, and I will cross-correlate a little bit this with what Ehud was talking about previously. So the setup is simple. First, let's see the number density of baryons, which is the key quantity here, is assumed to decrease as inverse radius squared. This is a special regime as Ehud was talking about, but this is related to the propagation of the jet inside a star. We are instead talking about the propagation of relativistic outflow, whatever is jet or not jet. Here we talk about spherical symmetry, but there is not a loss of generality because we always can assume there is some dependence on the angles. And here the jet is expanding freely in the, not in the medium, but in vacuum. Therefore, Lorentz factor should increase with radius, and the law of this increase of the radius of the Lorentz factor can be put also in principle in the power law form. And for radiative pressure dominating cases without any magnetic field, the Lorentz factor increases linearly with radius. So A parameter should be equal 1 in this case. Instead, if the flow is magnetized, it was shown that the A parameter could vary between 1/3 and 1. So a slower acceleration of the magnetized flows. So in the ultra, let's say, magnetized asymptotic, it will be 1/3, and less and less magnetized outflow will accelerate faster up to gamma proportional to the radius. And eventually, this acceleration will stop once the energy density of the outflow becomes less than the matter density. And in that case, sorry, not less, comparable to the matter density. In that case, the Lorentz factor will be constant, so there will be not further acceleration. And that is basically it. How is this related to the what Ehud was talking about previously? So if you look through the jet in the symmetry axis, you will get essentially relativistic jet, and the Lorentz factor will be proportional to radius initially, and will be proportional. It will be constant later on. This is after, of course, the jet broken out from the surface, because after the surface it doesn't meet any material in front. And instead, if you look at larger angles, the dynamics will be essentially the same, but the Lorentz factor reached at the constant phase would be different, would be lower, because the energy density will be smaller at the larger angles, and therefore Lorentz factor can, as actually Ehud showed, is a theta dependent quantity, so it's angle dependent quantity. In the symmetry axis, it is the highest, and outside the symmetry axis, it is decreasing, possibly as a power law. And we can look at different angles, and depending on the parameters we put in this simplified model, we can see what happens with the photospheric emission in this case. One point I have to mention is this intermittency of the jet, which is of course not modeled here. Jet is assumed to be, or outflow is assumed to be simply a constant in density and constant in energy at a given radius. And expanding, the density will decrease, like in this law here, inversely proportional to radius squared. But what is the key point in all this calculation is that we assume the outflow is finite in radii. Therefore, it is not infinite wind as assumed in many works on the photospheric emission. It is not either a geometrically infinitesimally small shell, it's assumed in other models. It has simply a finite wind, which is given by the parameter L here. So this is one of the parameters of the model. The optical depth computed in invariant way is given by this equation. So optical depth is the integral along the path of the photon of the cross-section of interaction. In this particular case, the interaction is the Compton scattering. This is the dominant interaction. Moreover, it's in Thomson regime. So for cross-section will be assumed to be a constant. The full flux of the outflow, the differential element of the space, and this integral should be related along the path of the photon. So put in a simpler form in this calculation, we have, simpler means basically spherically symmetric assumption. This is the only assumption done here. Theta is the angle between the radius vector and the propagation angle of the photon. Beta is the for the velocity of the outflow. So here we have the integral from emission radius up to radius where the photon experienced the last scattering of this expression. So this is exactly here where the calculation of the Novikov, Paczynski, and Abramowicz is essential, where this factor appears in the calculation, but it's actually followed just from this expression. If you write down this expression carefully. So this integral, in our particular case of the hydrodynamic model described above, result in three asymptotic solutions. All these asymptotic solutions are written here. In particular, in accelerating phase, here we find the photospheric radius. So if we equate the optical depth to unity, eventually here we can define the radius where the photon will be last scattered in the outflow. And this expression is written as a ratio to the initial radius of the outflow where it starts acceleration. So R0 here is the radius where Lorentz factor equals unity, where acceleration starts. So the photospheric radius is proportional to, let's talk now about the unmagnetized flow, putting A equal to 1, just to see the correspondence with the previous results. And if A equal 1, you can see that the photospheric radius is proportional to tau 0, which is initial opacity at the base of the flow, to power 1/3. And this is the famous accelerating asymptotic, where the outflow becomes transparent when it is still accelerating. In particular case, it can happen also when there are no baryons, but just electrons and positrons present in the outflow. In that case, there is no cost in error because electrons, positrons annihilate and emission happens still at accelerating phase. The standard infinite wind asymptotic is recovered as the second line, where the photospheric radius is proportional to initial opacity and inversely proportional to the Lorentz factor at the constant phase. And the final asymptotic of thin shell is recovered as the third possibility when the photospheric radius is the largest possible. So this initial opacity is exactly the quantity which comes from the total energy and the Lorentz factor observed, or variability timescale observed, which is parameterizing this unknown quantity. And this is exactly what enters, this parameter enters the opacity, the compactness arguments I was talking about previously. So typically this tau naught is huge in gamma ray bursts. It's about 10 to 11 in the weakest cases, up to 10 to 15, 16 in the strongest in energy cases. And this justifies that thermal emission actually must be trapped in the expanding outflow, and it eventually can be observed if conditions are right enough. So in another model where you assume the constant energy injection at the base of the outflow, L is luminosity, eta is again the dimensionless entropy quantity parameter, and that's it. So tau 0 is initial opacity, and you can see that the photospheric radius has a very different form as function of this of the parameters of the model. So if the outflow, and this is happens in most cases, if the outflow becomes transparent at the coastal phase, the two bottom asymptotic are the most relevant one. Now let's talk a little bit about the terminology. We introduced the photon thick and photon thin asymptotic. Basically, this means that in consider the infinite wind, therefore everything is static. So the photosphere is the static surface. So when photons propagating in this infinite wind eventually reach the surface, they decouple from the outflow. Everything happens at the same moment for all the photons in the outflow, and there is no boundary by definition in this infinite outflow. It goes up to infinity. Therefore, photons will be essentially emitted from a given surface. This is essentially the case when the outflow is thick enough, but we're not talking about geometrical thickness here. We are talking about thickness for photons propagating inside the outflow. Given relativistic effects here, we just call this photon thickness, so thickness for a photon propagating inside the outflow. Even for a finite wind, it could be geometrically thin, so thin shell at large radii, but still it could appear as long wind, essentially infinite wind for photons propagated inside. Opposite case is the photon thin, namely when we have the shell, or essentially part of the wind, which is thin enough that photons can reach its boundaries while they are propagating inside the outflow. Of course, in ultra-relativistic case, this appears to be a plausible condition, but it's not really proved that it is the only condition possible. Also, opposite condition can happen, namely that you can have thin shell, which is still looks like infinite wind for photon propagating inside it. To understand this better, I can show you this diagram on the left. This is a function of the depth inside the finite wind. The probability of photon decoupling yes, this is the probability of photon decoupling. So for photon thin cases, you see that the probability peaks at the boundaries of the wind, both inner boundary and outer boundary. Instead, for photon thick cases, the probability is essentially constant within the outflow. So the photon has equal chance to decouple from the outflow in any place inside it. This was obtained using Monte Carlo calculations, this result. And here you see also the probability of emission, probability density function, sorry, of emission of photons. This is for photon thick outflows as function of Lorentz factor, if I remember correctly. And this case is particularly infinite wind, so the probability falls out as 1/r². And this is essential to see, to find the effect of the larger angle photons from the photosphere. Instead, if a photon decouple at the photosphere, at the boundaries, the photon thin case, their probability has very different shape, and I will come back to this point later on. As function of parameters of the model, it can be shown that all three asymptotic cases are present in principle for various energies and variance factors typically assumed in gamma-reversed models. So all three asymptotic have to be considered and determined in particular all the parameters from the observation to see if we are in the right asymptotic. A few words also about the appearance of the photosphere, like in the star, you know perfectly this is a static surface. In our sun, it's quite sharp. In Betelgeuse, for example, the photosphere is very diffuse, but still static. Accelerating and Cosmology photosphere look very differently. They are dynamic. This is essential. These are just snapshots of the pictures, and they are also quite diffuse. So emission from different angles is essential. Now let's talk about the dynamics in geometry for a few moments, and then I will jump to the diffusive photospheres. So on the left, the photon thick case is present. I recall that this is similar to the infinite wind case, but again, infinite wind is static, has a static photosphere, which is represented here by this line, emitting line. On the vertical axis, there is the impact parameter, and on the horizontal axis, there is just radius. And R equal 1, S over R versus R photospheric equal 1 correspond to photospheric radius. So essential property of the relativistic photosphere has very different shape with respect to the static one. Static on the right here, or not static, sorry, this is photon thin case on the right, but for the static, the photosphere will appear like essentially with this shape. Instead, for relativistic wind, it appears like this. Why the optical depth is minimum along the symmetry axis? Why it is minimum? Simply because of this effect discovered by, or better, underlined by Novikov, Abramovich, and Paczynski, that along the line of sight, the mean free path is largest possible, is multiplied by gamma factor, and along any other angles, in particular orthogonal to the line of sight, the mean free path is divided by gamma. Therefore, there is a factor ratio gamma squared in two orthogonal directions, and therefore this explains why along the line of sight the optical depth is the minimum possible, and at larger angles it increases. And you can see, as I mentioned, the photosphere of finite wind is a dynamical surface, and here we show at different times by black lines the photosphere. Initially it appears similar to the photon thin case, but then later on it becomes more and more approaches the asymptotic shape of the wind. And by this dashed line, we show also 1 over gamma, the relativistic beaming angle, relativistic angle, okay? And this is simply not the angle of the jet, but this is the angle that can be seen at this angle. The maximum extension of the photosphere can be seen. Beyond this angle, the photon will never reach the observer. And by red, we show also the probability distribution function introduced before, and this is basically shows that the photon decoupling occurs a little bit before the photosphere, but comparable to this radius. Instead, if we come to the photon thin case, we see very different behavior. Yes, I forgot to mention the temperature gradient is shown here. So in principle, in the in the line of sight, the temperature is highest, and of course the largest angle is, the temperature is smaller. So what we observe is not a simple black body, a single black body, but a multicolor black body. Basically, it has to be computed the convolution of the emission of photons from different angles and different times that reach the observer at the same time, which is the equitemporal surface, which is also discussed a lot by Carlo Cianobianco and Professor Ruffini. And these equitemporal surfaces should be computed carefully for both photon-thick and photon-thin cases. For photon-thin case, the probability of emission is also peaking at some radius, but compared to the photon-thick, it is different radius. It is diffusion radius, which we'll come to in a moment. So what is diffusion radius? You know, the emission can happen like with early universe, for example. The first transparency of our universe is when the density become low enough and photons started to propagate in all the possible directions, and we see the remnants of these photons as the cosmic microwave background radiation today, which is very important for observations in cosmology. So same effect happens actually in photon thick cases, as I mentioned here. The emission happens everywhere. Sorry, the decoupling of photons happens everywhere in the outflow. And there is no particular radius where it is essential. Instead, in the photon thin case, the emission happens at the boundaries, and therefore photons have enough time to propagate to the boundaries and be last scattered there. What is the dynamics of photons in the optically thick medium? Because we're talking about the photosphere at the moment where the optical depth becomes finally approaches unity, but before it was high. Before the outflow is optically thick, the photons propagate essentially due to diffusion in such an outflow. Here we have to take into account that the outflow is expanding relativistically. All the calculations will therefore result taking into account the diffusion in a certain radius where the photon finally can reach by diffusion the boundary. Diffusion in the expanding and relativistically expanding, therefore density is decreasing, and the motion is relativistic in principle, and then photons propagate in such a medium. There is an analytic solution obtained for this situation, and the radius of diffusion, the radius where photons will eventually diffuse out to the boundary, will be given by this condition. It's different with respect to the photospheric radius, and it can be shown that it crucially depends on the parameter. We mentioned this in principle parameter when we divide both sides by tau 0, it will be a parameter which is less or larger than 1. So if it is larger than 1, then we find that the first line, the diffusion radius is smaller than the photospheric radius. What does it mean? It means that the photons will be transported to the boundary of the outflow before the optical depth falls down to 1. Therefore, it's really a diffusive process which determines the presence of the photosphere in this case. It's similar to the supernova, where in the supernova you have the emission trapped initially and generated initially by radiative species decay. Okay, and then this emission is transported, radiation is transported to the boundary and eventually emitted at the boundary. It takes a long time for this process to happen. Therefore, emission is not instantaneous. It is radiative transport involved here. And the only difference with the supernova is that this is relativistically expanding outflow, not non-relativistic like in supernova. To do the calculations, can we in principle determine what could be Lorentz factors in this case from the observation? We need several several inputs. One input is the temperature, how the temperature is in expanding outflow. Well, it is well known that during the acceleration, the temperature, observed temperature, is essentially constant due to energy decrease, but Lorentz boost, Doppler boost essentially. But when acceleration stops, the temperature is decreasing inversely proportional to radius 2/3, over 2/3, and this is one important point. Second point is that the luminosity in that case is decreasing with radius with the power -8/3. This is very strong decrease, and this has been used in argument, this expression, to say that if the photosphere is far away from the source of gamma burst, then there is no chance to detect this photosphere. This was essentially the argument why it was abandoned back in the 80s, where the theory, I'm sorry, in the 90s, where the theory was essentially done for this, and also recent measures discussed this point, and they even went so far to say that we must somehow revive this photospheric emission, and some dissipation was introduced in models, ad hoc dissipation mechanism, which can potentially generate more fresh photons in the outflows. And one example would be actually the last slides shown by Ehud NAKAR previously, which showed that if the outflow is intermittent, namely is variable, there will be internal shocks which will produce eventually dissipation inside outflow. The only difference, the only problem would be here that the efficiency of such shocks is known to be quite low, therefore it does not help much to increase the luminosity of the photospheric emission in this case. Anyway, let me go on. Another parameter is the so-called R parameter, which was first introduced by Pierre et al. In their work, and this is essentially observable quantities combined in a dimensionless form. So we have here the flux in black body, we have the observed temperature, and this could be combined to get this dimensionless number, which is related to the radius of emission and Lorentz factor of emission. Here, this parameter is of the order of 1. It's essential is to know the distance to the source. So once the redshift is measured, this R parameter and basically combination of observables can be related to the ratio of emission radius and Lorentz factor. So what has to be known here is either Lorentz factor or the emission radius. This can be retrieved, so it is also important that the initial radius, nozzle radius, sometimes called radius at the base of the outflow, is also a function only of observed parameters and some parameter gamma here, which can be usually assumed to be of the order of 1. Again, all this relies on the measurement of the distance to the source. Combining this parameter in relativistic case, gamma is larger than 1, much larger than 1, but as Landau used to say, if quantity is 3, this means much larger than 1. Therefore, we still can apply gamma much larger than 1 for quite small gamma compared to traditional cases measured in the prompt emission. And therefore, using this radius, for the radius of emission, we assume the diffusion radius, we can obtain the relation between the eta, the dimensionless entropy, which is the same as the Lorentz factor at the coasting phase, and we are at the coasting phase here, and the thickness of the outflow. So in principle, this is the final result, which relates the Lorentz factor at the diffusion radius at the photospheric radius for this outflow, and better, maybe I just want to underline this. Photospheric traditionally is defined as the radius where optical depth is equal to 1, but since the diffusion radius is smaller in this particular case, better we don't use the photospheric radius, we keep using the term diffusion radius. Okay, so we can find, knowing the observed parameters, we can find essentially the Lorentz factor if we know the thickness of the outflow. And the two limiting expression for Lorentz factor can be obtained assuming the minimum possible extension, which is equal to R0, initial radius of the outflow. And here we have this expression, and the maximum possible length of the extension of the outflow, which we equal to the diffusion radius. In that case, diffusion radius divided by the squared. And in that case, this is the condition of applicability of the photon peak asymptotic. In that case, we recover the photon peak asymptotic, which was obtained by Pear et al. In 2007. This is the expression traditionally used in the literature. We are going to use this expression in analysis of the cases which we discuss below. And now, why I mentioned already that since the luminosity of the photosphere decreases so fast with radius, there is little chance to see such a photospheric emission. This is true unless you have, for some reason, the decrease of non-thermal emission. And this is exactly what happens at, as I mentioned before, at the end of the prompt emission. There is strong decline of the emission. And exactly at this epoch, there is observation of thermal component in some of the gloss of gamma bursts. So using this information, typical temperature varies about 1 kiloelectron volt. And the typical duration of this emission is some tenths of seconds, can reach hundreds of seconds in some cases. So if we take this parameter as observable, and if we take the observed flux, observed temperature, we can measure Lorentz factor of this emission, assuming that this emerged from the diffusive photosphere. So there was a paper by Giovanna DAINOTTI in 2018 where they basically collected all the observational information about the black body component measured in the early afterglows of multiple gamma ray bursts. And I will comment briefly on two cases here, which can be considered as prototypical examples of these cases. So 090618, in this case, the Lorentz factor, which emerged from these two expressions, so we can give the larger Lorentz factor here and the smaller Lorentz factor here by these two expressions. So you can see that the smaller possible is 3, and the larger possible is about 40. So it can be in all in between these two limiting cases. Assuming that Lorentz factor, that the extension of the flow is the smallest possible, we find instead that the y parameter here, gamma parameter here is 5.7. Gamma parameter is the ratio between the total energy in the outflow to the energy emitted in gamma rays. So in principle, it's always larger than 1, but typically it's assumed to be 1. So it means that with this particular case, Lorentz factor can be quite small, up to a value of few. If we have instead another case, this is similar case, yes, to this one, 060218, the famous 060218. And in this case, we find that the Lorentz factor should be practically very small, up to 6. And if this is so small, this is a very good indication that this could be produced by the relativistic cocoons. This is certainly not hundreds as observed in the prompt emission. This is quite small. And you can see that in principle, Lorentz factor, even here of the order of 40, is quite large, but it can be observed, it can be produced in that regions close to the symmetry axis of the jet propagating inside the star. Therefore, we consider this and several other cases here as possible indications of the cocoons in gamma ray bursts, but these cocoons must be emitting not in the at the photosphere, but they must be emitting at the diffusion radius that we introduced before. I must say that in most of the calculations so far, theoretical calculations, the calculation of the photospheric emission in cocoons has been done assuming that the radiation is emitted at the photospheric radius. Only in few calculations which are doing Monte Carlo post-processing of numerical results, there they compute really the scattering of photon, find the last scattering position, and then determine the observed spectra. Instead, most theoretical works focus on the photospheric emission, traditional photospheric emission of ultra-relativistic outflows. And this is not good, as we show here, because in principle, we see that photons do not arrive to the photosphere. They are emitted earlier, where diffusion basically plays an important role. Well, I think I conclude just to mention that two groups of gamma ray burst energy from this analysis are present, one with gamma larger than 100 or of the order of 100, and this is more or less traditional photospheric emission, and instead gamma much less than 100, where the presence of cocoons is most likely. And well, this is it. You can read my conclusions. I think yes, I would go to this, and this is the list of publications. In particular, these results are based on the last publication in this list. I think I conclude. Thank you very much. I'm ready for questions.
Okay, thank you. Thank you, Gregory. If someone has questions, then just raise your hand and go on. Okay, just as a curiosity, the last one you mentioned in the conclusion that they are divisible by the gamma factor of 100. So what is special, maybe one before, gamma factor more than 100 and gamma factor less than 100? So what is particular of this?
Nothing special, yeah, just larger than 100 is a typical photon thick case. If we look at the diagram I showed before, we are in the, well, let me show you, this is better. You see, for example, here, if we are somewhere in this region larger than 100, we are most likely in the Costin photon thick case, and this is the traditional wind model adopted in the literature. But if we extend this diagram to smaller eta, okay, or smaller gamma, less than 100, we'll see that this region, Costin photon thin, is starting to pop up in the diagram, and this explains that for quite large, I mean, here we're talking about luminosities, isotropic luminosities in the prompt, not in the afterglow, okay? So this could be quite large. And if we are in this region, therefore it's very likely we encounter the outflow with relatively small Lorentz factors. And this, they happen exactly in the diffuse region, the photospheric emission.
Okay, clear, thank you.
Okay.
Some other questions? Okay, if no questions, we just thank again Gregory and move forward. Thank you. The next speaker should be Daphne Guetta, but I don't see her here. I asked the secretary to contact well in advance. Okay, so let me just wait for 1 minute. Meanwhile, I'll go and ask for the secretary. Just 1 minute.
Well, we will try to reach Daphne later on today or tomorrow. And let's close the session of today. Thanks. We can close the session of this morning.
Yes, I think we can close the session because of some problems.
Thank you, Yerlan, and we will ask Weta to come in the next days.
Okay, so we have now lunch break up to 3 o'clock, and then we will continue with three talks by Piran, Mavromatos, and Petrosan. Okay, see you then at 3 o'clock.
Thank you so much.
Thank you.
Thank you very much. See you later.